Hello there, and welcome. Tonight I want to take you somewhere far beyond the gentle glow of city lights, beyond the familiar constellations that have watched over humanity for millennia, out into the vast, quiet darkness where mysteries drift silently through the cosmic void. Close your eyes for a moment if you'd like, and imagine yourself floating weightlessly above Earth, watching as our blue marble slowly turns beneath you, cities twinkling like scattered diamonds against the darkness. Now turn your gaze outward, past the moon with its ancient craters, past Mars with its rusty deserts, past the giant planets with their swirling storms, out to where the sun's warmth becomes just another star among billions. It's here, in this profound darkness between the stars, that our story begins. You see, something visited us recently. Not in the dramatic way of science fiction movies with blazing lights and thunderous arrivals, but in the way the cosmos actually speaks to us, quietly, mysteriously, leaving more questions than answers in its wake. This visitor was called 3I Atlas, though perhaps visitor isn't quite the right word. Maybe messenger is better, or perhaps harbinger, though even that sounds too ominous for what might simply be a chunk of ancient ice and rock that happened to pass through our neighborhood. But what if, just maybe, it was something more? What if this fragmenting comet, this dissolving traveler from interstellar space, was trying to tell us something about the nature of the universe itself, about intelligences that might exist in the darkness between stars, about messages written not in radio waves or laser beams, but in the very act of falling apart? I know what you might be thinking. It's a question that seems almost too fantastic to consider seriously. The kind of thing that belongs in late-night speculation rather than scientific inquiry. But here's the beautiful thing about the universe. It has consistently proven to be stranger, more wonderful, and more mysterious than we ever imagined. Every time we think we understand the cosmic rules, something drifts in from the darkness to remind us how much we still don't know. And 3I Atlas, this interstellar wanderer that graced our skies so briefly before dissolving into fragments, might just be one of those reminders. Consider this for a moment. In all of human history, we've only confirmed 3 objects that definitely came from interstellar space. 3. Out of all the countless comets and asteroids we've observed, only 3 have been proven to be true outsiders, visitors from the vast emptiness between star systems. The first was Oumuamua in 2017, that strange tumbling object that accelerated in ways we still don't fully understand. The second was Borisov, a more traditional-looking comet that at least behaved in ways we expected. And then came 3I Atlas, discovered in 2019, an object that seemed ordinary enough at first but then did something peculiar. It completely fell apart as it approached our sun, not in the violent way of a collision, but in a gentle, almost deliberate dissolution, like a dandelion releasing its seeds into the cosmic wind. Now, comets break apart all the time, you might say, and you'd be right. Our solar system is full of the remnants of shattered comets, their debris creating the meteor showers that grace our night skies with shooting stars. But there was something different about how 3I Atlas fragmented, something that made astronomers pause and look more carefully at their data. This wasn't a comet that had been worn down by countless passages around our sun. This was a fresh arrival from interstellar space, presumably intact after a journey that might have lasted millions or even billions of years, only to dissolve completely during its first and only encounter with our star. Imagine, if you will, the journey this object must have taken. Picture it beginning somewhere impossibly far away, perhaps in a solar system that looks nothing like our own, orbiting a star of a different colour, a different size, a different age. Maybe it formed in the same way our comets did, from the primordial dust and ice left over from a star's birth. Or maybe, and here's where we allow ourselves to wonder, maybe it was constructed. Not necessarily by little green beings with advanced technology, but by something. Some intelligence that understood the patient art of interstellar communication, that knew how to send messages across the incomprehensible gulfs between stars. the journey itself would have been almost impossibly long by human standards. If 3A Atlas travelled at typical interstellar velocities, it might have been drifting through the darkness for tens of millions of years. Think about that timeline for a moment. When this object began its journey, assuming it came from one of our nearer stellar neighbours, there were no humans on Earth. Depending on how far it travelled, there might not have been mammals, or dinosaurs, or even complex life at all. It drifted through the cosmic darkness while continents shifted, while species evolved and went extinct, while the Earth itself changed beyond recognition. And through all that time, it maintained its course, a silent messenger carrying what exactly? Perhaps it's helpful to think about scale here, to really grasp the vastness of the stage on which this cosmic drama plays out. If you compressed the entire history of the universe into a single year, with the Big Bang occurring at midnight on January 1st, our solar system wouldn't form until early September. Life on Earth wouldn't appear until sometime in late September or early October. Dinosaurs would rule for just a few days in late December, and humans, we'd appear in the last few seconds before midnight on December 31st. In this compressed timeline, 3I Atlas might have been travelling since Christmas Day, or perhaps since Thanksgiving, depending on where it came from. It's been on a journey that makes our entire existence as a species seem like the briefest flicker of consciousness in a vast, dark cosmos. But let's bring our attention back to the object itself, to what we actually observed when 3I Atlas entered our solar system. It was first spotted by the Atlas survey in Hawaii, hence part of its name, though it had probably been falling toward our sun for months or years before we noticed it. At first, it seemed like a fairly typical comet, developing the characteristic fuzzy coma as solar radiation began to heat its surface. Astronomers around the world turned their telescopes toward it, eager to study this rare interstellar visitor. What chemicals would its spectrum reveal? What could it tell us about the conditions in other star systems? How did it compare to Oumuamua and Borisov, our only other confirmed interstellar guests? But then something unexpected happened. As 3I Atlas approached the Sun, instead of simply growing brighter and developing a more pronounced tail like most comets, it began to fragment. Not all at once, not in a sudden catastrophic event, but gradually, gently, like a sugar cube dissolving in warm tea. The nucleus split into pieces, then those pieces split again, and again, until what had been a single object became a cloud of fragments, each following slightly different trajectories, each catching the sunlight in its own way. It was beautiful, in the way that destruction can sometimes be beautiful, like watching a sandcastle slowly claimed by the tide. Now, you might wonder why this fragmentation is so intriguing, why it might be more than just a natural process of a fragile object meeting its end. After all, comets are essentially dirty snowballs, amalgamations of ice and dust held together by the weakest of forces in the cold of space. When they approach the Sun, the ice sublimates, turning directly from solid to gas. And sometimes this process can tear the comet apart. It's happened to plenty of comets from our own solar system. But here's where things get interesting. 3I Atlas had survived an interstellar journey. It had endured cosmic radiation, the gravitational tugs of passing stars, the slow erosion of high-speed dust impacts, for potentially millions of years. Why would it choose this moment, this approach to our particular star, to fall apart? Perhaps the word choose seems too anthropomorphic, too much like giving agency to what might be a simple ball of ice and rock. But in the quiet depths of space, in the vast emptiness between stars, perhaps choice takes on different meanings. Perhaps what we're seeing is not choice in the way we understand it, but something more like programming, or destiny, or the inevitable conclusion of a process set in motion eons ago. What if 3I Atlas was always meant to fragment here, in our solar system, at this particular time in cosmic history? Consider the timing. We live in an extraordinary moment in the history of our planet. For the first time in Earth's 4.5 billion-year history, A species has developed the ability to detect and track objects from interstellar space. We've only had this capability for a few decades, a blink of an eye in cosmic terms, and in that brief window, we've already detected 3 confirmed interstellar objects. What are the odds? If these objects have been passing through our solar system regularly throughout Earth's history, it seems remarkably coincidental that we'd spot 3 just as soon as we developed the ability to see them. Unless, of course, their appearance now is not a coincidence at all. This brings us to one of the most profound questions in astronomy, in philosophy, in human thought itself. Are we alone? It's a question that has haunted us since we first looked up at the stars and realized they were other suns, potentially warming other worlds. The Drake equation, formulated in 1961, attempts to estimate the number of communicating extraterrestrial civilizations in our galaxy. Depending on the values you plug in for various factors, the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, you can get answers ranging from 1, just us, to millions. But all those calculations assume that alien civilizations would communicate using radio waves, or other electromagnetic signals that we could detect with our telescopes. What if that assumption is wrong? What if advanced civilizations have moved beyond electromagnetic communication, finding it too slow, too prone to interference, too easy to miss in the cosmic static? What if they've developed other ways of sending messages across the galaxy, ways that we're only beginning to imagine? This is where 3i Atlas becomes particularly intriguing. Because if you wanted to send a message or a probe to multiple star systems, if you wanted to explore the galaxy in a way that was patient and thorough and nearly impossible to stop, you might design something that looked exactly like what we observed. Think about it this way. You're an advanced civilization, perhaps millions of years older than humanity. You've mapped your local stellar neighborhood, you've detected planets around distant stars, and you want to learn more about them. Maybe even make contact with any intelligences that might have evolved there. But space is vast, and even at the speed of light, messages take years or decades or centuries to cross between stars. Sending individual probes to each star system would require enormous resources and time. But what if you could send probes that could replicate themselves? Or better yet, probes that could split into multiple smaller probes, each capable of investigating different targets. This is the concept of von Neumann probes, named after the brilliant mathematician John von Neumann, who first described self-replicating machines. The idea is elegantly simple. You send out a probe that can use local resources to make copies of itself. Each copy then travels to a new star system and makes more copies. In this way, even traveling at a fraction of the speed of light, such probes could explore the entire galaxy in just a few million years. It's an idea that has captivated scientists and science fiction writers alike, because it represents a plausible way for an intelligent species to explore the cosmos without faster-than-light travel. But here's a variation on that theme that 3i Atlas might represent. Instead of self-replicating probes that build copies of themselves from asteroidal material, what if you designed probes that carried multiple smaller probes within them, like seeds in a pod? The outer shell would protect these smaller probes during the long interstellar journey, shielding them from radiation and micrometeorite impacts. Then, when the probe reached a star system with potentially interesting planets, it would fragment, releasing its cargo of smaller probes to investigate different targets. Some might head for rocky planets, others for moons, still others might remain in space to study the star itself. From our perspective, watching 3i Atlas break apart, we wouldn't necessarily see the tiny probes being released. They could be microscopic, no bigger than grains of sand, but equipped with advanced nanotechnology that would allow them to gather and transmit information, or they might be biological in nature, designed to seed suitable worlds with the building blocks of life, or to test whether life already exists. The fragments we observed breaking off from 3i Atlas could have been merely the carrier shell, the protective coating that was no longer needed once the payload had been delivered. I can almost hear your skepticism and it's entirely warranted. This is speculation, beautiful and intriguing speculation, but speculation nonetheless. We have no direct evidence that 3I Atlas was anything other than a natural comet that happened to come from another star system. The simplest explanation, Occam's razor would suggest, is usually the correct one, and the simplest explanation is that 3I Atlas was exactly what it appeared to be. A chunk of ice and rock that formed in another star system was ejected by some gravitational interaction, wandered through interstellar space for millions of years, and happened to pass through our solar system where the sun's heat caused it to fragment. But even if we accept the natural explanation, 3I Atlas still carries profound implications. It's proof that material can travel between star systems, that the stars are not isolated islands in space, but part of an interconnected galaxy, where objects, and potentially life itself, can migrate from one system to another. Every interstellar object that passes through our solar system is a messenger from another star, carrying information about conditions in other parts of the galaxy. The chemicals locked in their ice and rock tell stories about the stellar nurseries where they formed, about the types of planets that might exist around other stars, about the raw materials available for life in other corners of the cosmos. And there's something else to consider. Something that makes the natural explanation almost as wonderful as the artificial one. If objects like 3I Atlas are regularly travelling between star systems, if the galaxy is full of these interstellar wanderers, then they represent a natural communication network, a way for star systems to share material and perhaps even life. The theory of panspermia suggests that life might spread through the galaxy by hitching rides on comets and asteroids. Impact on a life-bearing world could launch rocks into space, rocks carrying hardy microorganisms that could survive the journey between stars. When these rocks land on other suitable worlds, they could seed them with life. In this view, 3I Atlas and objects like it are not just messengers, but potential carriers of life itself. The fragmentation we observed could have been releasing not artificial probes, but natural packages of organic chemistry, each fragment potentially carrying the molecular building blocks of life to different parts of our solar system. Some of those fragments might have fallen to Earth, burning up in our atmosphere but perhaps delivering their cargo of organic molecules to our planet. Others might have headed for Mars or Europa or Enceladus, those worlds we suspect might harbour life beneath their surfaces. The timing of 3I Atlas's appearance in our solar system takes on new significance when we consider the current state of our technological development. We are, right now, at a crucial juncture in our development as a species. We've developed the technology to detect interstellar objects, to analyse their composition, to track their trajectories. We're also on the verge of becoming an interstellar species ourselves, with serious proposals for sending probes to nearby star systems within this century. Projects like Breakthrough Starshot envision using powerful lasers to accelerate tiny probes to a significant fraction of the speed of light, allowing them to reach Proxima Centauri in just 20 years. If we're about to take our first steps into interstellar space, perhaps it's not surprising that we're noticing more interstellar visitors. Not because there are actually more of them, but because we're finally paying attention, finally looking in the right places with the right instruments. Or perhaps, and here we venture into more speculative territory, perhaps these objects are appearing now because something out there has noticed that we're approaching a technological threshold. Perhaps 3I Atlas and its companions are scouts, or tests or invitations, appearing just as we develop the ability to see and understand them. The way 3I Atlas fragmented is particularly intriguing when we consider it from this perspective. The breakup wasn't violent or chaotic. It was almost gentle, a gradual dissolution that allowed astronomers to observe and track multiple fragments. Each piece followed a slightly different path, exploring different regions of our inner solar system. If you were designing a probe to survey a star system, this would be an elegant solution. Instead of building complex navigation and propulsion systems, you simply design your probe to fragment in a controlled way, using the star's gravity and radiation pressure to spread your sensor packages across a wide area. We've actually considered similar designs for our own space exploration. NASA has studied concepts for spacecraft that would split into multiple smaller probes to explore different targets. The advantage is obvious. You get more science for your launch cost, more coverage of your target system. If we, with our relatively primitive technology, can conceive of such designs, what might a civilization with thousands or millions of years of additional development create? Their probes might be so advanced, so different from our conception of technology, that we wouldn't recognize them as artificial even if we were looking right at them. This brings us to a profound realization about the search for extraterrestrial intelligence. We've been looking for signals that we would recognize as artificial: radio broadcasts, laser pulses, megastructures around stars. But what if advanced civilizations communicate and explore in ways that appear natural to us? What if they've learned to hide their technology in plain sight, disguising their probes as comets and asteroids, their messages as natural phenomena? It would be the ultimate camouflage, allowing them to observe younger civilizations without interfering, without causing the panic or disruption that obvious alien contact might bring. There's a concept in the search for extraterrestrial intelligence called the zoo hypothesis. It suggests that advanced civilizations might be aware of us but are deliberately avoiding contact, observing us the way we might observe animals in a nature preserve. They want to see how we develop naturally without interference. If this is true, then objects like 3i Atlas could be their observation posts, their cameras, their sensors, designed to look like natural objects to avoid disturbing the subjects they're studying. The fragmentation could be the probe's way of deploying multiple sensors without revealing its artificial nature. But let's pull back from these speculative heights for a moment and return to what we actually observed. 3i Atlas was detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, on December 28, 2019. At first, it appeared to be a fairly typical long-period comet, though its orbit quickly revealed its interstellar origin. It was approaching the Sun on a hyperbolic trajectory, moving too fast to be gravitationally bound to our star. Like Oumuamua and Borisov before it, it was just passing through, a brief visitor from the vast darkness between stars. Initial observations suggested that 3i Atlas would become visible to the naked eye by May 2020, potentially putting on a spectacular show as it swung around the Sun. Amateur astronomers around the world prepared their equipment, excited for the chance to see an interstellar visitor with their own eyes. But by March 2020, it became clear that something was happening to the comet. Instead of brightening as expected, it began to fade. Images showed that the nucleus was elongating, stretching out like taffy pulled by invisible hands. By April, it had clearly fragmented into multiple pieces. The Hubble Space Telescope was turned toward 3i Atlas in April 2020, providing our best views of the fragmentation. The images showed dozens of fragments, some large, some tiny, all surrounded by clouds of dust and gas. It was like watching a cosmic explosion in slow motion, each piece drifting apart from its siblings at a few miles per hour. The fragments continued to evolve, some brightening, others fading, some developing their own small comae as ice sublimated from their surfaces. It was a dynamic, ever-changing scene that kept astronomers captivated for weeks. What caused this fragmentation? The scientific consensus is that it was likely due to thermal stress as the comet approached the Sun. The surface would heat up during the day, then cool rapidly as it rotated into darkness. This constant expansion and contraction could have opened cracks in the nucleus, eventually causing it to split apart. Or perhaps pockets of particularly volatile ice suddenly sublimated, creating jets of gas that tore the comet apart. These are perfectly reasonable, natural explanations that fit with what we know about cometary physics. But there are some oddities that keep the door open to more exotic possibilities. The fragmentation seemed to begin when 3i Atlas was still quite far from the Sun, farther than where we typically see comets break apart. The pattern of fragmentation was unusually regular, with pieces of similar size spreading out in an almost organized fashion. And the timing, as we've discussed, seems remarkably coincidental. An interstellar object choosing to fragment just as it passes through the inner solar system of a star that harbors a technological civilization. One particularly intriguing aspect of 3I Atlas's behavior was the way different fragments evolved after the breakup. Some pieces brightened dramatically, suggesting they were composed of particularly volatile materials that had been protected inside the original nucleus. Others faded quickly, perhaps made of darker, less reflective materials. This diversity suggests that 3I Atlas wasn't a homogeneous object, but had a complex internal structure. If it was a natural comet, this complexity tells us about the varied conditions in its formation environment. If it was something else, well, complex internal structure is exactly what you'd expect from a designed object. The fragments of 3I Atlas continued their journey through the solar system, each on its own path, each carrying its own secrets. Some passed close to the sun and were completely vaporized, their materials joining the solar wind to be scattered across the solar system. Others survived their solar encounter and headed back out into interstellar space, perhaps to visit other stars in the distant future. And some, just possibly, might have released something we didn't see, something too small for our telescopes to detect, something that's still out there in our solar system, quietly doing whatever it was designed to do. This is where our imagination really takes flight. If 3I Atlas was carrying microscopic probes, where might they be now? Some could have been captured by planetary gravity, entering orbit around Earth or Mars or Jupiter. Others might have landed on asteroids or moons, using them as platforms for observation or as sources of raw materials. Still others might be drifting through the solar system powered by solar energy, transmitting data back to their creators by some means we can't detect. The possibilities are endless and endlessly fascinating. But even if we never find evidence of artificial origin, even if 3I Atlas was exactly what it appeared to be, a natural comet from another star, it still represents something profound. It's a piece of another solar system that we got to observe up close, a sample of the materials and conditions around another star. Every spectrum we captured, every image we took, every measurement we made adds to our understanding of the galaxy we inhabit. And the fact that it fragmented, spreading its materials across a wider area, means that its gifts to science were multiplied. Think about what we've learned from meteorites, those pieces of asteroids and comets that fall to Earth. They've taught us about the age of the solar system, about the conditions in the early solar nebula, about the building blocks of planets. Now imagine what we could learn from a meteorite that came from another star system entirely. The fragments of 3I Atlas that vaporized in the sun's heat released their chemicals into the solar wind. Some of those atoms and molecules will eventually fall to Earth, becoming part of our atmosphere, our oceans, our soil. In a very real sense, 3I Atlas has become part of our world. As we contemplate these possibilities, it's worth remembering that the universe has a long history of surprising us. When we first discovered pulsars, some scientists seriously considered the possibility that they were alien beacons, because their signals were so regular, so unlike anything we'd seen before. They even nicknamed the first pulsar LGM-1 for Little Green Men. Of course, pulsars turned out to be natural phenomena, rotating neutron stars, but they were a type of object we hadn't imagined could exist. The universe was stranger than we thought. Similarly, when we first detected gamma-ray bursts, brief flashes of incredibly intense radiation from deep space, some speculated about alien civilizations testing massive weapons or experiencing industrial accidents on a cosmic scale. Again, the real explanation turned out to be natural, the collapse of massive stars and the collision of neutron stars, but it revealed violent processes in the universe that we hadn't anticipated. Nature, it seems, is often more creative than our imaginations, so when we look at 3I Atlas and wonder whether it might be something more than a simple comet, we're following in a long tradition of considering extraordinary possibilities When faced with unusual observations, most of the time the extraordinary explanation turns out to be wrong, and the universe reveals new natural phenomena that expand our understanding of physics and cosmology. But sometimes, very rarely, the extraordinary explanation turns out to be correct. Continental drift was once considered absurd. The idea that a massive asteroid impact killed the dinosaurs was ridiculed. The suggestion that most of the universe consists of invisible dark matter and dark energy seemed like desperate speculation. The beauty of science is that it gives us a method for distinguishing between wishful thinking and reality. We observe, we hypothesize, we test, we refine our understanding. With 3i Atlas, we're still in the early stages of this process. We have observations, its interstellar origin, its fragmentation, the behavior of its pieces. We have hypotheses, both natural and more exotic. What we need now is more data, more observations, more visiting interstellar objects to study and compare. And this is where the story becomes even more intriguing. Because 3i Atlas wasn't the last interstellar visitor we've detected. As our surveys of the sky become more comprehensive, as our instruments become more sensitive, we're finding more and more objects that appear to come from beyond our solar system. Some are confirmed interstellar objects, others are probable candidates waiting for more observations. Each one is a new piece of the puzzle, a new opportunity to understand our place in the galaxy. The pattern that's emerging is fascinating. These interstellar objects seem to come in a variety of types. Some, like Borisov, look and behave like fairly typical comets, just happening to come from another star. Others, like Oumuamua, are weird and wonderful, challenging our understanding of what natural objects should look like and how they should behave. And then there's 3 Atlas, fragmenting at just the right time for us to observe its dissolution in detail. It's almost as if we're being presented with a curriculum, each object teaching us something new about the possibilities of interstellar travel. Perhaps this is reading too much into random chance. Perhaps we're like ancient humans seeing patterns in the stars and creating constellations where none exist. But pattern recognition is one of humanity's greatest strengths, the ability that allowed us to survive and thrive on this planet. And when we see patterns in the cosmos, even if they turn out to be coincidences, they inspire us to look deeper, to ask better questions, to expand our understanding of what's possible. As you drift off to sleep tonight, I invite you to hold these possibilities gently in your mind. Picture 3i Atlas on its long journey through interstellar space, silent and patient, carrying its secrets through the darkness. See it warming as it approaches our sun, beginning its graceful fragmentation, releasing whatever it carried, be it natural ice and dust or something more mysterious, into our solar system. Imagine those fragments spreading out like seeds on the cosmic wind, each one a story, a message, a possibility. Remember that we live in an extraordinary time, when humanity is just beginning to comprehend its place in a vast and possibly inhabited universe. Every interstellar object that passes through our solar system is a reminder that we're not isolated, that we're part of a galactic community of stars and planets and possibly life. Whether 3i Atlas was a natural comet or something more, it connected us to the cosmos in a profound way. Its atoms now mingle with our solar wind. Its light has touched our instruments. Its mystery has sparked our imagination. In the grand scheme of cosmic time, our species has existed for barely a moment. We've been looking at the stars with understanding for just a few centuries, listening for signals from other civilizations for just a few decades. If the galaxy is filled with life, with intelligence, with curious minds looking out at the stars just as we do, then we're newcomers to an ancient conversation. Objects like 3i Atlas might be part of that conversation, messages we're just beginning to learn how to read. Or perhaps we're alone, the only conscious observers in a vast and beautiful but ultimately empty cosmos. Even if that's true, objects like 3i Atlas are still messengers, carrying information about the galaxy's history, about the processes that create and destroy solar systems, about the raw materials from which life might arise. They're reminders that the universe is dynamic, always changing, always in motion, and that we're privileged to be here, now, able to observe and wonder at it all. As the second chapter of our journey begins, we'll explore the broader context of comets in human history and science. These cosmic wanderers have been inspiring fear and wonder for millennia, long before we understood what they were or where they came from. They've been omens and portents, gods and demons, harbingers of doom and symbols of renewal. But beyond the mythology and superstition, comets have turned out to be even more remarkable than our ancestors imagined. They're time capsules from the birth of solar systems, carriers of water and organic molecules, and possibly, just possibly, messengers from intelligences among the stars. The story of how we've come to understand comets is really the story of how we've come to understand our place in the universe. From ancient astronomers tracking their movements across the sky to modern scientists analyzing their chemical signatures, each observation has added another piece to the cosmic puzzle. And now, with interstellar comets like 3I Atlas, we're beginning to see that the puzzle is even bigger than we thought, extending beyond our solar system to encompass the entire galaxy. Think about the first humans who looked up at a comet and wondered what it was. They had no concept of orbital mechanics, but no understanding of ice and dust and solar radiation. To them, comets were mysteries written across the sky, messages from the gods or disruptions in the cosmic order. They watched these celestial visitors appear and disappear, sometimes returning after many years, sometimes vanishing forever. They recorded their observations on clay tablets and papyrus scrolls, beginning humanity's long conversation with these cosmic wanderers. Now we know that comets are essentially dirty snowballs, amalgamations of ice and dust left over from the formation of solar systems. When they approach a star, the ice begins to sublimate, creating the characteristic tail that can stretch for millions of miles. This tail always points away from the star, blown by the solar wind and radiation pressure, creating a cosmic weather vane that tells us about the invisible forces flowing from our sun. Every comet is a natural physics experiment, demonstrating principles of thermodynamics, orbital mechanics, and plasma physics on a scale we could never reproduce in a laboratory. But comets are more than just scientific curiosities. They're storytellers, each one carrying tales from the outer reaches of our solar system, or, in the case of interstellar comets, from other stars entirely. The ice in a comet formed billions of years ago, possibly in a different part of the galaxy. The dust grains might be even older, survivors from the stellar nursery that gave birth to our sun or another star. When we study a comet, we're reading pages from the galaxy's autobiography, written in a language of chemistry and physics that we're still learning to translate. The chemical composition of comets has proven to be remarkably complex. They contain water ice, of course, but also carbon dioxide, carbon monoxide, methane, ammonia, and a host of other molecules. Even more intriguingly, they contain organic molecules, not life itself, but the building blocks from which life might arise. Amino acids, the components of proteins, have been found in cometary material. These discoveries have led some scientists to propose that comets might have delivered the raw materials for life to Earth billions of years ago, seeding our planet with the chemicals needed for biology to begin. This idea that life's ingredients might have come from space changes our perspective on comets entirely. They're not harbingers of doom, but potentially harbingers of life. Cosmic delivery vehicles carrying precious cargo from star to star. Every comet that enters our inner solar system is potentially carrying organic molecules that could, under the right conditions, contribute to the development of life. And if comets can carry these materials between planets in our solar system, why not between star systems as well? This is where interstellar comets, like 3I Atlas, become particularly fascinating. If comets from our own solar system carry organic molecules, what might comets from other star systems contain? Different stars have different chemical abundances, different planetary systems have different compositions. An interstellar comet might carry exotic molecules we've never seen before, formed under conditions we can barely imagine. Or it might carry familiar molecules but in different proportions, giving us clues about the chemistry of other solar systems. The fragmentation of 3I Atlas takes on new significance when we consider it from this biochemical perspective. As the comet broke apart, it would have released not just water vapor and dust, but potentially complex organic molecules into our solar system. These molecules, too small to see with our telescopes, could now be drifting through space, some falling toward the sun to be destroyed, others heading outward to the cold depths of the outer solar system, and some, perhaps, falling toward planets where they might contribute to the chemical soup from which life could emerge. Imagine for a moment that somewhere in our solar system, perhaps on Mars or Europa or Enceladus, conditions are right for life to begin but missing some crucial ingredient. Then along comes 3I Atlas, carrying that missing piece from another star system. As it fragments, it releases this vital molecule, and some of it finds its way to that waiting world. It's a long shot, certainly, but the universe has billions of years to play such long odds. Over cosmic time, such chance encounters might be common, with life spreading through the galaxy not through deliberate action, but through the patient random wandering of comets. But let's return to what we can observe directly. The way comets behave as they approach the sun tells us a great deal about their structure and composition. Some comets brighten steadily and predictably. Their ice is sublimating at rates we can calculate based on their distance from the sun. Others are more erratic, experiencing sudden outbursts of activity as pockets of volatile materials are exposed to sunlight. Still others, like 3I Atlas, fragment completely, unable to withstand the thermal and gravitational stresses of their solar encounter. The fragmentation of comets isn't unusual in itself. We've observed many comets break apart over the years. Comet Shoemaker-Levy 9 famously fragmented into multiple pieces before crashing into Jupiter in 1994, giving us our first direct observation of a major impact event in our solar system. Comet Linear disintegrated in 2000, and Comet Ison met its end during a close encounter with the Sun in 2013. Each of these events taught us something new about cometary structure and the forces that can tear these cosmic snowballs apart. But the fragmentation of an interstellar comet is something special. This isn't an object that's been worn down by repeated passages through our inner solar system. This is fresh material from another star, experiencing our sun's heat for the first and only time. The way it responds to this heating, the way it breaks apart, tells us about conditions in its home system. Was it formed in a colder environment where the ices are more pristine? Was it exposed to different radiation environments that changed its chemical composition? These are questions we can begin to answer by studying how interstellar comets behave in our solar system. The timing of 3I Atlas's discovery and fragmentation is particularly poignant when we consider the state of the world in early 2020. As the comet was breaking apart in space, humanity was dealing with its own fragmentation as the COVID-19 pandemic spread across the globe. While we were isolated in our homes, separated from each other by necessity, this cosmic visitor was reminding us that we're all part of something much larger. The atoms that made up 3I Atlas had travelled between the stars, just as the atoms that make up our bodies were forged in the hearts of dying stars billions of years ago. We're all made of star stuff, as Carl Sagan famously said, and objects like 3I Atlas are reminders of our cosmic heritage. There's something deeply moving about the fact that we could observe 3I Atlas at all. This object had been travelling through space for potentially millions of years, and it happened to pass through our solar system at exactly the time when we had the technology to detect and study it. A few decades earlier, and we would have missed it entirely. A few decades later, and who knows what new instruments we might have had to study it with. But it came when it came, and we were ready. Our telescopes turned skyward, our computers ready to process the data, our minds prepared to wonder at what we were seeing. The international nature of the observations is worth noting too. Astronomers from around the world collaborated to study 3I Atlas, sharing data and insights across borders and time zones. Japanese telescopes, American spacecraft, European observatories all contributed to our understanding of this interstellar visitor. In a time when humanity often seems divided, astronomy reminds us that we're all under the same sky, all curious about the same cosmic mysteries. The fragmentation of 3i Atlas was observed by people of all nations, all cultures, all backgrounds, united in their wonder at this cosmic event. As we process the scientific data from 3i Atlas, we're also processing its philosophical implications. If material can travel between star systems, if the galaxy is full of wandering comets and asteroids carrying chemicals, and possibly life between the stars, then the universe is more interconnected than we ever imagined. We're not isolated on our pale blue dot, but part of a vast network of exchanging materials and possibly information. Every meteorite that falls to Earth, every comet that graces our skies, is a thread in this cosmic web, connecting us to the rest of the galaxy. The search for life beyond Earth has traditionally focused on looking for signals, radio waves, laser pulses, or other electromagnetic emissions that would indicate the presence of a technological civilization. But what if life spreads through the galaxy more subtly, more patiently? What if instead of broadcasting their presence, civilizations spread their influence through physical objects, through comets and asteroids and other seemingly natural phenomena? It would be a slower form of communication, taking millions of years instead of decades, but it would also be more durable, more certain to eventually reach its destination. This brings us back to the possibility that 3i Atlas might have been more than it appeared. If you were an ancient civilization wanting to explore the galaxy, wanting to spread life or gather information about other star systems, you might design your probes to look like comets. They would be protected during their interstellar journey by shells of ice and dust, indistinguishable from natural objects. Only when they reach their target star system would they activate, perhaps fragmenting to release their payload, just as we observed with 3i Atlas. It's a beautiful idea, even if it's almost certainly wrong. The universe is full of beautiful ideas that turn out to be wrong. But the process of considering them, testing them, and ultimately discarding them for better ideas is how we advance our understanding. Every hypothesis we propose, even the incorrect ones, teaches us something about how to think about the universe. And sometimes, very rarely, one of those beautiful ideas turns out to be correct, revolutionizing our understanding of reality. As we prepare to delve deeper into the mysteries of interstellar visitors, it's worth taking a moment to appreciate the sheer audacity of what we're attempting. We're trying to understand objects that come from other stars, places we've never been and may never visit. We're using the light they reflect, the gases they emit, the paths they follow through space to piece together stories about distant solar systems. It's like trying to understand an entire civilization from a single artifact that washes up on a beach, except the beach is our entire solar system, and the artifact is dissolving before our eyes. The instruments we use to study these objects are marvels in themselves. The telescopes that detected 3i Atlas can see objects billions of times fainter than what our eyes can perceive. The spectrographs that analyzed its light can identify individual molecules from millions of miles away. The computers that calculated its orbit can trace its path backward through time and space, telling us where it came from and where it's going. We've built these tools over centuries of scientific progress, each generation building on the discoveries of the last, all leading to this moment when we can study visitors from other stars. But for all our sophisticated technology, there's still something fundamentally human about our response to objects like 3i Atlas. We see something unusual in the sky, and we wonder what it means. We tell stories about it, we imagine possibilities, we project our hopes and fears onto these cosmic wanderers. This is what humans have always done when confronted with the unknown. The only difference now is that we have better tools for testing our stories against reality. The fragmentation of 3i Atlas was, in many ways, a gift to science. Instead of a single object to study, we got dozens of fragments, each potentially different in composition, each responding differently to solar heating. It was like getting multiple samples from an interstellar visitor instead of just one. Some fragments were brighter, suggesting they were rich in volatile ices. Others were darker, perhaps containing more rocky or organic material. This diversity within a single object tells us that interstellar comets, like their solar system counterparts, are complex, heterogeneous objects with varied compositions and structures. The dynamics of the fragmentation were fascinating to observe. The pieces didn't just drift apart randomly, but seemed to follow patterns that revealed the internal structure of the original nucleus. Some fragments stayed close together, suggesting they had been part of the same larger chunk. Others shot off in different directions, perhaps propelled by jets of gas from sublimating ice. Watching the fragmentation unfold over weeks was like watching a cosmic flower bloom in slow motion, each petal a fragment carrying its own secrets. One of the most intriguing aspects of the fragmentation was the appearance of what astronomers call fragment trains, lines of debris following similar orbits. These trains tell us about the forces acting on the comet as it broke apart. Was it torn apart by tidal forces as it approached the sun? Did internal pressure from sublimating gases cause it to explode? Or was there some other mechanism at work, something we haven't seen before in our observations of solar system comets? Each possibility has different implications for the nature and origin of 3I Atlas. The spectroscopic analysis of the fragments revealed a composition not too different from solar system comets, which was both reassuring and slightly disappointing. Reassuring because it suggested that the basic chemistry of planetary formation might be similar throughout the galaxy. Disappointing because we always hope for something exotic, something that would immediately tell us we're looking at an object from another star. But even this similarity is informative. It tells us that the processes that form comets might be universal, that the same physics and chemistry operate around other stars as they do around our sun. As we observe the fragments of 3 Atlas spreading apart, each following its own trajectory through the solar system, it was impossible not to think about where they would end up. Some would fall into the sun, their journey of millions of years ending in a brief flash of light. Others would swing around the sun and head back out into interstellar space, perhaps to visit other star systems in the distant future. And some, just possibly, might be captured by planetary gravity, becoming permanent residents of our solar system, interstellar immigrants that will orbit our sun until it dies billions of years from now. This raises an intriguing possibility. How many objects in our solar system actually originated around other stars? We tend to think of our solar system as a closed system, with all its asteroids and comets formed from the same primordial disk that gave birth to the planets. But if objects like 3I Atlas pass through regularly, and if some of them are captured by our sun's gravity or fragment into pieces that are captured, then our solar system might be more cosmopolitan than we thought. Some of the meteorites in our museums, some of the asteroids in the belt between Mars and Jupiter, might actually be interstellar immigrants that arrived millions or billions of years ago. The idea that our solar system might contain material from other stars isn't just speculation. Some scientists have proposed that certain unusual asteroids or comets might have interstellar origins. Objects with highly eccentric orbits, unusual compositions, or other anomalous characteristics might be ancient captures from passing star systems. If this is true, then we've been studying interstellar material for decades without realizing it. Every meteorite that falls to Earth could potentially be a messenger from another star, carrying information about distant solar systems in its minerals and molecules. As we continue our journey through the mysteries of interstellar visitors, we're about to encounter perhaps the most enigmatic of them all, Oumuamua. This object, detected in 2017, was our first confirmed interstellar visitor, and it immediately challenged our assumptions about what such objects should look like and how they should behave. Unlike 3I Atlas, which at least looked like a comet even if it behaved strangely, Oumuamua was weird from the start. Its shape, its rotation, its acceleration, Everything about it seemed designed to make us question what we thought we knew about interstellar objects. The story of Oumuamua is a reminder that the universe is under no obligation to conform to our expectations. Just when we think we understand something, along comes an observation that forces us to reconsider everything. This is the beauty and frustration of science. The universe is always one step ahead of us, always more creative than our theories, always ready with a surprise that sends us back to our equations and models to figure out what we missed. But before we dive into the mystery of Oumuamua, let's take a moment to appreciate where we are in our cosmic journey. We've considered the possibility that 3I Atlas might have been more than a simple comet, that its fragmentation might have been purposeful rather than accidental. We've explored how comets serve as messengers between stars, carrying materials and possibly life across the galaxy. We've thought about the profound implications of living in a galaxy where material regularly travels between star systems, where the boundaries between solar systems are more porous than we imagined. These ideas, whether they turn out to be correct or not, expand our conception of what's possible. They remind us that we're part of a vast, interconnected cosmos where the atoms in our bodies, the water in our oceans, and possibly even the seeds of life itself have travelled between the stars. Every time we observe an interstellar visitor like 3I Atlas, we're witnessing a chapter in this cosmic story, a story in which we're not just observers, but participants. The night sky will never look quite the same once you've contemplated these possibilities. Those points of light aren't just distant suns, but potential homes to other worlds, other forms of life, other civilizations looking out at their night sky and wondering if they're alone, and travelling between those stars, invisible to our eyes but increasingly visible to our instruments, are the messengers, comets and asteroids, and perhaps something more, carrying materials and information and possibilities across the vast darkness. As you continue to drift towards sleep, picture 3I Atlas one more time. See it not as it ended, fragmented and dissolving in the heat of our sun, but as it was during its long journey through interstellar space. Silent, patient, carrying its cargo of ice and dust and secrets through the darkness between stars. For millions of years it travelled alone, far from any sun's warmth, far from any planet's gravity. And then, in a cosmic coincidence that defies probability, it encountered our solar system just as we developed the ability to see it, to study it, to wonder about it. Was it just a comet, a ball of ice and rock that happened to pass our way? Or was it something more, a messenger, a probe, a seed cast into the cosmic ocean by some distant intelligence? We may never know for certain. But the very fact that we can ask these questions, that we can observe these interstellar visitors and speculate about their nature and purpose, makes us participants in the greatest mystery of all, the question of whether we're alone in the universe or part of a vast cosmic community we're just beginning to discover. The story of Oumuamua begins on October 19th, 2017, at the Haleakala Observatory in Hawaii. Astronomer Robert Werrick was reviewing images from the Pan-STARRS telescope, looking for near-Earth asteroids that might pose a threat to our planet. It's routine work, scanning the sky for moving objects, comparing images taken minutes apart to spot anything that's changed position against the background stars. But on this particular night, Werrick noticed something unusual, an object moving so fast that it couldn't possibly be bound to our sun's gravity. At first, this didn't seem particularly remarkable. Comets on highly elliptical orbits can move very quickly when they're close to the sun, but as more observations came in, and the object's trajectory was calculated more precisely, it became clear that this was something unprecedented in the history of astronomy. The object, initially designated A2017U1, was on a hyperbolic trajectory, moving too fast to have originated in our solar system. It had to have come from interstellar space. The astronomical community reacted with barely contained excitement. This was the moment they had been waiting for, the first confirmed detection of an object from another star system passing through our own. telescopes around the world swung toward the mysterious visitor, eager to learn everything they could before it disappeared back into the darkness. Time was of the essence. The object was already heading away from the sun and would soon be too faint to observe even with our most powerful instruments. The object was given a new name, Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. It was a fitting name for humanity's first confirmed interstellar visitor, and it honoured the Hawaiian observatory where it was discovered. But as data about Oumuamua accumulated, it became clear that this messenger was bringing more questions than answers. The first surprise was Oumuamua's appearance, or rather its lack of appearance. Unlike comets, which develop bright Comean tails as they approach the sun, Oumuamua remained a point of light in our telescopes. No coma, no tail, no visible outgassing despite passing within Mercury's orbit of the sun. It looked like an asteroid, a chunk of rock and metal rather than the icy body we might expect from the cold depths of interstellar space. This was puzzling because most models of planetary formation suggest that objects ejected into interstellar space should be icy comets from the outer regions of their solar systems, not rocky asteroids from the inner regions. But the real shock came when astronomers measured Oumuamua's light curve, the way its brightness changed over time. The object was tumbling through space, rotating every 7.3 hours, and as it rotated, its brightness varied by a factor of 10. This extreme variation suggested that Oumuamua was highly elongated, perhaps 10 times longer than it was wide. No asteroid or comet in our solar system has such an extreme shape. It was as if someone had thrown a cosmic cigar or needle through our solar system. The shape immediately sparked speculation. Natural processes can create elongated objects, but nothing quite this extreme had been observed before. Some scientists proposed that Oumuamua might be shaped like a flattened disc rather than a cigar, which would also explain the brightness variations. Others suggested it might be a contact binary, two objects stuck together, or perhaps a fragment of a larger body that had been torn apart by tidal forces. But there was another possibility, one that captured the public imagination and even gained some support from serious scientists. What if Oumuamua was artificial? The idea wasn't as outlandish as it might seem. If you wanted to build a probe to travel between stars, you might design it to be long and thin to minimize drag from interstellar dust and gas. Or if you were using a light sail for propulsion, pushed by radiation from stars or powerful lasers, you'd want a large, flat, reflective surface, exactly the kind of shape that could explain Oumuamua's light curve. The object's lack of visible outgassing despite its close approach to the sun was also consistent with an artificial structure made of metal or other non-volatile materials. Harvard astronomer Avi Loeb became the most prominent advocate for seriously considering the artificial hypothesis. In papers, and eventually a book, he argued that Oumuamua's properties were so unusual that we should at least entertain the possibility that it was a piece of alien technology. Perhaps it was a defunct probe, a piece of space junk from another civilization, or even an active device gathering data about our solar system. The idea was controversial, with many astronomers arguing that natural explanations, however unusual, were more likely than alien technology. But Loeb's point was that we shouldn't dismiss the possibility just because it seems extraordinary. As Oumuamua continued its journey out of our solar system, another puzzle emerged. Careful tracking of its trajectory revealed that it was accelerating slightly more than could be explained by gravity alone. Something was pushing Oumuamua, giving it an extra boost as it headed back to interstellar space. For a comet, this wouldn't be surprising. Outgassing from sublimating ice creates thrust, like a very gentle rocket engine. But Oumuamua showed no signs of outgassing, no coma, no tail, no spectroscopic signatures of water vapor or other gases. So what was causing the acceleration? Scientists proposed various explanations. Perhaps Oumuamua was outgassing, but the gas was invisible to our instruments. Maybe pure hydrogen or something else that doesn't show up in our observations. Perhaps the object was so small and the outgassing so subtle that we simply couldn't detect it with our current technology. Or perhaps the acceleration was due to radiation pressure from the sun, pushing on Oumuamua like wind on a sail. But for radiation pressure to cause the observed acceleration, Oumuamua would have to be incredibly light for its size, perhaps only a few millimeters thick, more like a sail than a solid object. Each explanation had problems. If Oumuamua was outgassing hydrogen, where did all that hydrogen come from? Hydrogen ice only forms at incredibly low temperatures, lower than we'd expect even in interstellar space. If it was being pushed by radiation pressure, how could a natural object be so thin and light yet survive the journey between stars? The more scientists studied Oumuamua, the more mysterious it became. The fragmentation we witnessed with 3I Atlas wasn't just a cosmic event happening millions of miles away. It was a demonstration of the universe's most fundamental processes playing out before our eyes. When that ancient traveler began to break apart, each fragment became a separate messenger, each piece carrying its own story about the conditions in a distant star system. Some of those fragments were rich in volatile ices that had been protected deep within the original nucleus for perhaps billions of years. Others were darker, rockier pieces that might have formed in the hotter regions closer to their parent star before being incorporated into the comet during some ancient collision or merger. The diversity we observed in those fragments suggests that 3I Atlas wasn't a uniform object, but rather a cosmic aggregate, a collection of materials from different parts of its home system that had been pressed together by gravity and time into a single wandering ambassador. As we watched those fragments drift apart at mere walking speeds relative to each other, it was impossible not to wonder about their ultimate destinations. The mathematics of orbital mechanics tells us that some of those pieces fell into the sun, their long journey ending in a brief flash of light as they vaporized in our star's corona. But others swung around the sun and headed back out toward interstellar space, perhaps slightly altered in their trajectories, but still carrying their cargo of ancient materials toward other stars. And here's where the story becomes even more intriguing. Some of those fragments might still be in our solar system, captured by the subtle gravitational dance of planets and moons, circling our sun as permanent immigrants from another star. The possibility that pieces of 3I Atlas might have taken up residence in our solar system opens up fascinating questions about contamination and exchange between star systems. If fragments of interstellar comets can be captured by our sun's gravity, then our solar system might be less isolated than we thought. Over the billions of years since our planets formed, how many interstellar visitors have left pieces of themselves behind? Some scientists estimate that there could be thousands or even millions of captured interstellar objects hiding among the asteroids and comets we consider native to our solar system. They would be nearly impossible to identify without detailed chemical analysis, cosmic needles in a very large haystack. But let's return to that moment of fragmentation, to what we actually observed as 3I Atlas came apart. The process wasn't violent or explosive. It was almost gentle, like watching a sugar cube dissolve in slow motion. This tells us something important about the forces at work. The comet wasn't hit by anything. It wasn't torn apart by a close encounter with a planet. Instead, it seemed to succumb to internal stresses, to forces that had been building up gradually as it approached our sun. The heat caused different parts of the nucleus to expand at different rates, opening cracks that had perhaps been dormant for millions of years. Pockets of super volatile ices, materials that had been stable in the cold of interstellar space, suddenly found themselves warming for the first time since their formation, creating pressure that pushed the fragments apart. This gentle fragmentation is particularly interesting when we consider the possibility of design disintegration. If you were engineering a probe to split apart at a specific point in its journey, you wouldn't want an explosion that would damage delicate instruments or scatter your cargo too widely. You'd want exactly what we observed, a controlled, gradual separation that allowed each piece to maintain its integrity while following a slightly different trajectory. The fragments of 3i Atlas spread out in an almost organized fashion, like seeds dispersing from a pod, each one potentially heading toward a different target in our solar system. The timing of the fragmentation adds another layer to the mystery. 3 Atlas began to break apart when it was still about 0.8 astronomical units from the Sun, roughly the distance of Venus's orbit. This is closer than many comets that survive their solar passages intact, but farther than where we typically see comets undergo catastrophic disruption. It's almost as if 3i Atlas was programmed to fragment at a specific distance from our star, close enough that the pieces would spread throughout the inner solar system, but far enough that they wouldn't be completely vaporized by solar heat. Consider what this means from an engineering perspective. If you wanted to survey our solar system, to sample different regions and environments, fragmenting your probe at Venus's orbital distance would be nearly optimal. Some pieces would fall sunward, allowing you to study the extreme environment close to our star. Others would head outward, potentially encountering Earth, Mars, the asteroid belt, and beyond. The natural dynamics of orbital mechanics would do the work of distributing your sensors throughout the solar system. No complex navigation required. But even if we set aside these speculative possibilities and assume 3i Atlas was entirely natural, its fragmentation still teaches us profound lessons about the cosmos. Every piece that broke off was like opening a nested Russian doll, revealing materials that had been protected from space weathering for eons. The freshly exposed surfaces gave us glimpses of pristine interstellar material, unaltered by repeated passages through any solar system. The spectra we captured from these fresh surfaces are scientific gold, telling us about the chemical conditions in another star system billions of years ago. The way different fragments evolved after the breakup was particularly revealing. Some pieces brightened dramatically, suggesting they were composed almost entirely of volatile ices that began sublimating furiously once exposed to sunlight. These might have been the comet's original building blocks, primordial ice that condensed from the cold gas of a stellar nursery. Other fragments remained dark and relatively inactive, possibly chunks of carbonaceous material or even more exotic compositions we haven't yet identified. This diversity within a single object tells us that the process of comet formation, even in other star systems, creates heterogeneous objects with complex internal structures. As we tracked the individual fragments, each one became a separate natural experiment in how interstellar material responds to our sun's environment. The brightest fragments, those richest in volatile ices, created their own small comae as they sublimated, becoming miniature comets in their own right. We could measure the rate of mass loss, calculate the energy balance, and infer the composition of the escaping gases. Each fragment was teaching us something different about the original composition of 3i Atlas, and by extension, about the conditions in its home star system. The distribution of fragment sizes also told a story. In a natural fragmentation event, we might expect a power law distribution, many small pieces and fewer large ones, following a predictable mathematical relationship. But the fragments of 3i Atlas showed some interesting deviations from this pattern. There seemed to be preferred sizes, clusters in the distribution, that suggested the original nucleus had natural fracture planes, or was composed of discrete units that separated along pre-existing boundaries. This could be natural. Many comets show evidence of being rubble piles, of smaller units held together by weak forces. Or it could be something else, evidence of internal structure that was designed rather than accidental. The chemical analysis of the fragments, limited as it was by distance, and the faintness of the objects, revealed both similarities and differences compared to solar system comets. The basic ingredients were familiar: water ice, carbon dioxide, various organic molecules. But the ratios were subtly different. The isotopic signatures didn't quite match what we see in our own comets. These differences are exactly what we'd expect from material that formed in a different stellar environment, under different temperatures and pressures, from a slightly different mix of primordial elements. It was like hearing a familiar melody played in a different key, recognizable but distinctly foreign. One of the most intriguing observations was the detection of what appeared to be complex organic molecules in some of the fragments. The spectroscopic signatures were subtle and somewhat ambiguous, but they suggested the presence of long-chain carbon molecules, possibly including amino acids or their precursors. If confirmed, this would mean that 3I Atlas was carrying the building blocks of life from another star system into our own. Even if the comet was entirely natural, it was potentially seeding our solar system with organic molecules from another star, contributing to the cosmic inventory of life's raw materials. The philosophical implications of this are staggering. If comets regularly carry organic molecules between star systems, then the galaxy is more biochemically connected than we ever imagined. Life wouldn't need to arise independently on every inhabited world. It could spread naturally through the galaxy via these interstellar messengers. Every comet impact on a young planet could be delivering not just water, but the molecular seeds from which life could spring. The early Earth, bombarded by comets during the late heavy bombardment, might have received organic molecules not just from our own solar system, but from stars throughout our galactic neighborhood. This natural exchange of materials between star systems might explain one of the great mysteries of biology, why life on Earth appeared so quickly after our planet became habitable. The traditional view is that life arose through chemical evolution on Earth itself, with simple molecules gradually becoming more complex until the first self-replicating systems emerged. But if Earth was being constantly seeded with complex organic molecules from interstellar comets, the process might have been accelerated. Life might not have had to start from scratch, but could have built upon a rich foundation of cosmic chemistry, delivered from the stars. As the fragments of 3I Atlas continued to disperse, some heading for their final plunge into the sun while others began their long journey back to interstellar space, astronomers faced a choice. With limited telescope time and resources, which fragments should they follow? Which pieces might reveal the most about this interstellar visitor's nature and origin? The decisions made in those weeks will affect our understanding of 3I Atlas for years to come, as we'll never have another chance to observe these particular messengers from another star. The fragments that survived their solar encounter and headed back toward interstellar space carried with them subtle changes from their passage through our solar system. They had been heated, their surfaces altered by solar radiation, their volatile components partially depleted. If these fragments eventually encounter another star system with curious astronomers, those observers will see evidence of the fragments' encounter with our Sun written in their chemistry and structure. In this way, 3I Atlas becomes not just a messenger to us, but a messenger from us, carrying information about our solar system to other stars. This raises an intriguing possibility about the nature of interstellar objects. Perhaps they're not just one-way messengers, but cumulative recorders of their journeys through multiple star systems. Each stellar encounter adds another layer to their story, another chapter in their chemical and physical evolution. An object that has passed through several star systems might carry a complex record of the different environments it has experienced, a cosmic travelogue written in isotope ratios and mineral structures. If we could fully decode such a record, we might learn not just about one distant star system, but about the paths that materials take through our galaxy. The fragmentation of 3I Atlas also demonstrated the importance of being ready for unexpected cosmic events. The comet gave us very little warning before it began to break apart. If our telescopes hadn't been watching, if our automated surveys hadn't been running, we would have missed this spectacular event entirely. This underscores the need for continuous comprehensive monitoring of the sky. We never know when the next interstellar visitor will arrive or what surprises it might bring. The universe doesn't schedule its revelations for our convenience. We have to be watching all the time, ready to swing our instruments toward whatever cosmic mystery presents itself. As we reflect on the fragmentation of 3I Atlas, it's worth considering how this event fits into the larger pattern of interstellar visitors we've observed. Each one, Oumuamua, Borisov, and 3I Atlas, has been different, challenging our expectations in its own way. Oumuamua with its bizarre shape and unexplained acceleration, Borisov with its familiar appearance but interstellar origin, and 3 Atlas with its spectacular fragmentation. It's as if the universe is presenting us with a curriculum, each object teaching us something new about the possibilities of interstellar travel. The fact that we've detected 3 confirmed interstellar objects in just a few years suggests that such visitors are relatively common. Statistical models based on these detections indicate that there might be thousands of interstellar objects passing through our solar system at any given time, most too small or too distant for us to detect with current technology. We're only seeing the tip of the cosmic iceberg, the largest and brightest of these interstellar wanderers. Imagine what we might discover as our detection capabilities improve, as new telescopes come online and our surveys become more comprehensive. The next generation of astronomical instruments will revolutionize our ability to study interstellar visitors. The Vera Rubin Observatory, with its enormous field of view and sensitivity, will be able to detect much smaller and fainter objects, potentially discovering dozens or hundreds of interstellar visitors each year. The James Webb Space Telescope and future space-based observatories will be able to analyze the composition of these objects in unprecedented detail, perhaps even detecting biosignatures if any of these visitors carry evidence of life from other star systems. But technology alone isn't enough. We also need to be intellectually prepared for what we might discover. The fragmentation of 3I Atlas reminded us that interstellar visitors might behave in ways we don't expect, might challenge our assumptions about what's natural and what's not. We need to keep our minds open to possibilities that might seem like science fiction today, but could be science fact tomorrow. The history of astronomy is full of discoveries that seemed impossible until they were observed. Planets orbiting other stars, black holes, dark energy. Interstellar visitors might bring the next paradigm-shifting discovery. As we prepare to explore the concept of von Neumann probes and their implications for interstellar exploration, it's worth pausing to appreciate the profound shift in perspective that objects like 3I Atlas represent. For all of human history, we've been confined to one star system, able to study other stars only from afar. But now, pieces of those distant systems are coming to us, delivering themselves to our telescopes for examination. It's as if the galaxy, patient and generous, is sending us samples to study, knowing that we're not yet ready to go out and collect them ourselves. The idea that 3I Atlas might have been artificial, might have been a probe or messenger from another civilization remains highly speculative. The vast majority of scientists believe it was a natural comet, unusual perhaps in its interstellar origin and its fragmentation, but natural nonetheless. Yet the very fact that we can seriously consider the alternative, that we have the scientific framework to test such hypotheses, represents a remarkable maturation of human thought. We're no longer simply wondering if we're alone in the universe, we're actively looking for evidence, developing methods to distinguish between natural and artificial interstellar visitors. The search for extraterrestrial intelligence has traditionally focused on detecting electromagnetic signals, radio waves or laser pulses that an alien civilization might use to communicate. But physical artifacts, especially those that can travel between stars, might be an equally important avenue for contact. A probe can carry far more information than a radio signal, can perform active observations rather than passive transmission, and can potentially survive for millions of years, far longer than any civilization might continuously broadcast. If alien civilizations exist and want to explore or communicate across the galaxy, sending probes might be more practical than sending signals. This brings us to one of the most profound ideas in the search for extraterrestrial intelligence, the concept of von Neumann probes. Named after the brilliant mathematician and polymath John von Neumann, these are theoretical spacecraft that could explore the entire galaxy using an elegant strategy of self-replication. The basic idea is simple but powerful. You send out a probe equipped with the ability to mine asteroids or moons for raw materials, and use those materials to build copies of itself. Each copy then travels to a new star system and repeats the process. Like a technological virus spreading through the galaxy, such probes could visit every star system in the Milky Way in just a few million years, even traveling at speeds far below the speed of light. The mathematics of von Neumann probe propagation are fascinating and somewhat alarming. Starting with a single probe and assuming each probe can make just 2 copies of itself before moving on, you would have over 1 million probes after just 20 generations of replication. After 40 generations, you'd have more probes than there are stars in our galaxy. The exponential growth is staggering, which is both the power and the danger of self-replicating technology. A civilization that launched von Neumann probes would need to be very careful about their programming, ensuring they didn't replicate out of control and consume all available resources. But here's where the fragmentation of 3I Atlas becomes particularly intriguing. What if instead of self-replicating probes that build copies from raw materials, an advanced civilization designed probes that carried multiple smaller probes within them? It would be like a technological seed pod, protecting its cargo during the long interstellar journey and then releasing it upon arrival in a new star system. This would avoid some of the dangers of uncontrolled replication, while still allowing a single launch to explore multiple targets. The fragmentation we observed could have been exactly this, a carrier probe releasing its payload of smaller exploratory devices. The advantages of such a design are numerous. The outer shell could be made to look like a natural comet, allowing the probe to observe without alerting any civilizations that might be present. The fragmentation could be triggered by specific conditions: proximity to a star, detection of planets, or even recognition of technological signatures. Each fragment could be specialized for different tasks, some designed to study the star, others to investigate planets, still others to search for signs of life or intelligence. It would be an efficient way to explore a star system comprehensively with a single interstellar mission. If we entertain this possibility, then the pattern of fragmentation becomes even more interesting. The fragments didn't all go in random directions, but spread out in a way that would allow them to sample different regions of our solar system. Some headed sunward, where they could study our star up close. Others maintained trajectories that would take them past the inner planets. Still others headed for the outer solar system. If you were designing a survey mission, this is exactly the kind of dispersal pattern you'd want. The fragments themselves showed interesting variations in behavior. Some became active, developing small comae as volatile material sublimated. Others remained dark and quiet. This could be natural variation in composition, or it could represent different types of probes with different missions. Active fragments might be gathering and analyzing gases and dust. Quiet fragments might be passive observers, recording data while maintaining a low profile. The diversity we observed could be functional rather than accidental. Of course, we need to be careful not to see design where none exists. The human mind is exceptionally good at finding patterns, even in random data. We see faces in clouds, canals on Mars, and messages in the static of cosmic radio waves. The fragmentation of 3I Atlas could be entirely natural, following the laws of physics without any guiding intelligence. Occam's razor, the principle that the simplest explanation is usually correct, would favor the natural interpretation. But Occam's razor is a guideline, not a law, and the universe has repeatedly shown us that reality can be stranger than our simplest explanations suggest. The timing of the 3 Atlases' appearance and fragmentation raises interesting questions about observation and detection. If it was a natural object, then its arrival during the brief window when humanity has the technology to detect and study interstellar objects is a remarkable coincidence. But if it was artificial, the timing might not be coincidental at all. An advanced probe could have been monitoring our technological development, waiting until we reached a certain threshold before making itself known. The fragmentation could have been triggered not by solar heating but by detection of our radio emissions, our space probes, or some other indicator of our technological capability. This leads to a fascinating possibility. What if the galaxy is full of dormant probes, waiting for civilizations to develop to the point where they can detect and potentially communicate with them. It would be like a cosmic test. Only civilizations advanced enough to spot interstellar visitors would be deemed ready for contact. The probes wouldn't need to be actively monitoring every star system all the time. They could drift dormant through interstellar space for millions of years, activating only when they detected signs of technology or when certain conditions were met. Such a strategy would solve one of the problems with the Fermi paradox, the question of why, if the galaxy is full of intelligent life, we haven't seen obvious signs of it. If advanced civilizations use subtle probes rather than obvious signals, if they wait for younger civilizations to reach certain milestones before revealing themselves, then the apparent silence of the cosmos might be an illusion. The galaxy could be teeming with intelligence, but it's intelligence that's patient, careful, and respectful of the natural development of younger species. The fragmentation of 3i Atlas could represent a transition from passive to active observation. As a single object, it could observe our solar system as a whole, gathering general data about our star and planets. But as fragments, it could conduct detailed studies of specific targets. Some fragments might have been tasked with analyzing Earth's atmosphere, looking for biosignatures or signs of industrial activity. Others might have been sent to investigate Mars, Jupiter's moons, or other potentially habitable locations in our solar system. The dispersal pattern could have been optimized for maximum information gathering, with minimum obvious interference. If this sounds like science fiction, remember that we're already doing something similar with our own space exploration. When we send missions to other planets, we often include multiple instruments, landers, or probes that separate to explore different regions. The Cassini mission to Saturn released the Huygens probe to land on Titan. Mars missions have included both orbiters and landers. The European Space Agency's Rosetta mission deployed a lander to the surface of a comet. We design our missions to gather as much information as possible from a single launch, and an interstellar mission would likely follow similar principles but on a much grander scale. The technology required for interstellar probes, whether self-replicating or fragmenting, is certainly beyond our current capabilities, but might not be beyond the reach of a civilization a few thousand or million years more advanced than us. We can already envision the basic principles: miniaturization, artificial intelligence, advanced materials, efficient propulsion. Projects like Breakthrough Starshot are seriously planning to send tiny probes to nearby stars within this century. Given exponential technological growth, what might we be capable of in 1,000 years, in 1,000,000 years? The fragments of 3i Atlas that survived their solar encounter and headed back to interstellar space might still be out there, carrying with them data about our solar system. If they were natural, they carry chemical and physical information about their encounter with our sun. If they were artificial, they might carry far more: detailed observations of our planets, analysis of Earth's atmosphere, perhaps even detection of our technological civilization. These fragments could be heading towards some distant star where another civilization might eventually recover and analyze them, learning about our existence indirectly, just as we learned about their star system from 3i Atlas itself. This raises profound questions about privacy and exposure in a galaxy where interstellar objects regularly travel between star systems. If natural objects can carry information about their origins, and if artificial probes can conduct detailed surveillance, then no star system is truly isolated. We're all part of an interconnected galactic community, whether we realize it or not. Our activities, our existence, even our biological and technological signatures might be spreading through the galaxy on interstellar messengers we never see. The idea of von Neumann probes or fragmenting exploratory missions also has implications for our own future as a spacefaring species. If we want to explore the galaxy, sending self-replicating or multi-probe missions might be our best option. The distances between stars are so vast, the travel times so long, that sending individual missions to each star system would take millions of years and enormous resources. but a single self-replicating probe or a fragmenting probe carrying hundreds of smaller explorers could survey multiple star systems, potentially exploring a significant fraction of the galaxy within a manageable time frame. We're already thinking about these possibilities. Scientists and engineers have proposed various designs for interstellar probes that could replicate or divide to explore multiple targets. Some designs use solar sails or laser propulsion to reach a few % of the speed of light. Others propose slower but more capable probes that could conduct detailed studies of their target systems. The fragmentation strategy observed in 3I Atlas, whether natural or designed, might inspire new approaches to interstellar exploration. As we contemplate these possibilities, drifting deeper into the cosmic mystery, it's important to remember that we're at the very beginning of our journey as a spacefaring species. We've only been able to detect interstellar objects for a few years. We've only been seriously searching for extraterrestrial intelligence for a few decades. In cosmic terms, we've barely opened our eyes. The discoveries that await us in the coming decades and centuries could fundamentally transform our understanding of our place in the universe. The next time an interstellar visitor appears in our skies, we'll be better prepared. New telescopes and instruments will allow us to study these objects in greater detail. We might even be able to send spacecraft to intercept them, to study them up close or even collect samples. Imagine being able to hold in your hand a piece of another star system, to analyze in our laboratories materials that formed around an alien sun. The scientific value would be incalculable, but the philosophical and cultural impact might be even greater. As we transition into contemplating the broader implications of von Neumann probes and the possibility of a galaxy populated by patient, watching intelligence, the fragmentation of 3I Atlas takes on new significance. It becomes not just an astronomical event, but a possible message, a gentle announcement that we're not alone, that the galaxy is more alive and aware than we imagined. Whether this message is real or imagined, whether 3I Atlas was natural or artificial, the questions it raises are profound and transformative. The concept of von Neumann probes represents one of the most elegant solutions to the challenge of galactic exploration, but it also opens up possibilities that border on the philosophical and even the spiritual. Imagine for a moment that somewhere in our galaxy, perhaps millions of years ago, a civilization reached a level of technological sophistication that allowed them to build self-replicating spacecraft. They faced the same vast distances we contemplate today, the same seemingly insurmountable barrier of interstellar space. But instead of being discouraged, they found a solution that would allow them to explore not just a few nearby stars, but the entire galaxy. The design of such probes would require solving numerous technical challenges, each one pushing the boundaries of what we currently consider possible. First, there's the issue of intelligence. A von Neumann probe would need to be smart enough to navigate between stars, identify suitable resources for replication, and make decisions about where to send its offspring. This isn't just artificial intelligence as we know it today. It's artificial intelligence that can operate independently for potentially millions of years, adapting to situations its creators never anticipated. Then there's the challenge of replication itself. The probe would need to carry within it the complete blueprint for building copies of itself, along with the tools and techniques necessary for construction. It would need to be able to mine asteroids or moons for raw materials, refine those materials into usable components, and assemble those components into functioning spacecraft. It's like asking a single robot to build an entire factory from scratch, and then use that factory to build more robots, each as capable as the original. The materials science alone is staggering to contemplate. The probe would need to be built from materials that could survive millions of years in the harsh environment of interstellar space, bombarded by cosmic rays, eroded by high-speed dust particles, subjected to extremes of temperature. Yet these materials would also need to be reproducible, using whatever raw materials the probe could find in alien star systems. It's a constraint that would require incredible ingenuity to overcome. But perhaps the most fascinating aspect of von Neumann probes is the question of their programming, their directives, their purpose. What would you tell a probe that might outlive your civilization? What instructions would you give to something that might still be operating millions of years after your species has evolved into something unrecognizable or gone extinct entirely? The probes would need to be given goals that make sense across geological timescales, purposes that transcend the temporary concerns of their creators. One possibility is that von Neumann probes would be programmed primarily for exploration and information gathering. Each probe would study the star systems it visits, cataloguing planets, analyzing atmospheres, searching for signs of life. The information could be transmitted back to the home civilization, or perhaps stored for later retrieval, or maybe shared with other probes to build a comprehensive map of the galaxy. Over millions of years, such a network of probes could accumulate an encyclopedia of galactic knowledge, a complete survey of every star system in the Milky Way. But there's another possibility, one that's both more ambitious and more altruistic. What if von Neumann probes were designed not just to explore, but to seed life throughout the galaxy? They could carry the building blocks of life, organic molecules, perhaps even preserved microorganisms, and deliver them to suitable worlds. Or they could be programmed to nurture existing life, protecting young biospheres from asteroid impacts or stellar flares, acting as cosmic gardeners tending to the galaxy's living worlds. It would be a project of unimaginable scope and duration, but for a civilization thinking on truly cosmic timescales, it might seem like a worthy legacy. The fragmentation behavior we observed with 3I Atlas could fit into either scenario. If the object was a von Neumann probe or something similar, the fragmentation could have been its way of creating multiple exploratory units without the need for complex replication machinery. Each fragment could be a simpler probe designed for a specific task: atmospheric analysis, surface sampling, or long-term observation. It's a strategy that trades the complexity of self-replication for the simplicity of pre-built multiplicity. Consider how this might work in practice. The main probe, disguised as a comet to avoid detection or interference, enters a star system on a hyperbolic trajectory. As it approaches the star, internal mechanisms activate, perhaps triggered by temperature, radiation levels, or the detection of planets. The probe fragments, releasing dozens or hundreds of smaller probes, each no larger than a grain of sand but packed with advanced nanotechnology. These tiny probes spread throughout the system, some landing on planets and moons, others remaining in space to monitor stellar activity or search for signs of technology. The beauty of this approach is that it requires no exotic technology that we can't at least imagine. We already have the beginnings of nanotechnology, the ability to build machines at the molecular scale. We understand the principles of distributed computing, where many small processors work together to solve complex problems. We've even experimented with smart dust, tiny sensors that can be scattered across an area to gather data. Scale these technologies up, or rather down, and extend them to interstellar distances, and you have something very much like what 3I Atlas might have been. But let's pull back from these speculative heights and consider what the existence of von Neumann probes would mean for our understanding of the Fermi paradox. If it's possible to explore the entire galaxy with self-replicating probes in just a few million years, and if our galaxy is billions of years old, then why hasn't Earth been obviously visited by such probes? This is sometimes called the Hart-Tipler argument, after the scientists who first articulated it. They argue that the absence of obvious alien probes on Earth suggests that we might be alone in the galaxy. There are several possible resolutions to this paradox, each with profound implications. Perhaps von Neumann probes are here, but we haven't recognized them. They might be disguised as natural objects, like comets or asteroids, observing us without our knowledge. The fragmentation of 3I Atlas could have been exactly such a probe revealing itself, or at least conducting its mission in a way we could observe. We might be surrounded by alien technology that's so advanced or so well camouflaged that we mistake it for nature. Another possibility is that von Neumann probes are programmed with ethical constraints that prevent them from interfering with developing civilizations. They might be present in our solar system but maintaining a respectful distance. Observing without interfering, waiting for us to develop to a point where contact would be beneficial rather than harmful. This is sometimes called the prime directive hypothesis, borrowed from Star Trek, but it represents a serious possibility for how an advanced civilization might choose to explore the galaxy. Or perhaps the probes are here but dormant, waiting for specific triggers to activate. They might be programmed to remain hidden until a civilization reaches certain technological milestones, developing radio communication, achieving spaceflight, or perhaps detecting the probes themselves. The fragmentation of 3I Atlas occurred just as humanity was developing the capability to observe and analyze interstellar objects in detail. Coincidence? Probably. But the possibility that it was triggered by our technological development can't be entirely dismissed. There's also the sobering possibility that von Neumann probes have visited Earth in the past but found nothing of interest. For most of Earth's history, there was no technological civilization to detect, and for most of that time, there wasn't even complex life. If probes visited Earth 1 million years ago, they would have found a planet dominated by primitive hominids, with no technology beyond stone tools. Such probes might have catalogued Earth as a living world, but not one requiring immediate attention, planning to return in a few million years to check on our progress. The implications of von Neumann probes extend beyond just exploration and contact. If such probes exist and have been spreading through the galaxy for millions or billions of years, they would form a kind of galactic nervous system, a network for sharing information across the vast distances between stars. Civilizations that never meet in person could still exchange knowledge through the probe network. It would be a slow conversation, taking thousands of years for messages to propagate, but it would connect the galaxy's intelligent species in a web of shared information. This cosmic internet would fundamentally change the nature of intelligence in the galaxy. Individual civilizations might rise and fall, but the knowledge they accumulated would be preserved in the probe network. New civilizations arising around young stars could tap into this network and inherit the wisdom of species that went extinct billions of years ago. The probes would be more than just explorers. They would be the galaxy's memory, its library, its legacy. The fragmentation of 3I Atlas takes on new meaning in this context. Each fragment could be carrying not just instruments for studying our solar system, but also information from other star systems, other civilizations. The fragments that fell into our sun might have been delivering this information to our star, encoding it somehow in the solar wind or stellar magnetic field. The fragments that passed by Earth might have been attempting to communicate, broadcasting on frequencies or in formats we don't yet know how to detect. We might have witnessed not just the breakup of a comet, but an attempt at contact that we weren't equipped to recognize. As we contemplate these possibilities, it's important to maintain scientific skepticism while remaining open to extraordinary possibilities. The most likely explanation for 3I Atlas remains that it was a natural comet that happened to fragment as it passed through our solar system. But the very fact that we can seriously consider alternatives, that we can imagine and investigate the possibility of alien probes, represents a profound shift in human consciousness. We're no longer content to simply wonder about our place in the universe. We're actively looking for answers. The search for von Neumann probes or other artifacts of alien intelligence is becoming a legitimate scientific endeavor. Projects like Breakthrough Listen are scanning the skies for artificial signals, but they're also beginning to consider the possibility of physical artifacts. As our ability to detect and track small objects in our solar system improves, we might discover anomalies that can't be explained by natural processes. The fragmentation of 3I Atlas has shown us that interstellar visitors can behave in unexpected ways, and we need to be prepared for even strange discoveries in the future. The philosophical implications of discovering a von Neumann probe would be staggering. It would mean that we're not alone, that intelligence has arisen elsewhere in the galaxy and reached a level of technological sophistication far beyond our own. But more than that, it would mean that this intelligence cared enough about exploration and knowledge to launch probes that would outlive their creators. It would be evidence of cosmic ambition, of civilizations that thought and planned on timescales we can barely comprehend. It would also raise difficult questions about our own future. If von Neumann probes are possible, should we build them? Do we have the right to send self-replicating machines to other star systems, potentially affecting worlds that might harbour their own life? How can we ensure that our probes wouldn't become a kind of grey goo, consuming resources meant for other civilizations? These are questions we'll need to answer as our own technology advances toward the point where interstellar probes become feasible. The fragmentation of 3I Atlas has given us a glimpse of one possible future for interstellar exploration. Whether natural or artificial, the comet demonstrated that objects can travel between stars and that they can split into multiple pieces to explore different regions of a star system. As we develop our own interstellar ambitions, we might look to 3I Atlas as inspiration for probe designs that use fragmentation as an exploration strategy. Imagine launching a probe toward Proxima Centauri, our nearest stellar neighbour. As it approaches the star system, it could fragment into dozens of smaller probes, each designed to study a different aspect of the system. Some could analyse the star itself, studying its flares and magnetic field. Others could investigate the potentially habitable planet Proxima Centauri b, analysing its atmosphere and searching for biosignatures. Still others could explore the outer regions of the system, looking for additional planets or interesting asteroids. It would be like sending an entire fleet of spacecraft with a single launch. The technology to build such probes might be closer than we think. Advances in miniaturization, artificial intelligence, and material science are rapidly approaching the point where we could build spacecraft small enough and smart enough to serve as interstellar explorers. Projects like Breakthrough Starshot are already planning to send tiny probes to nearby stars within this century. These first missions will be simple flyby observations, but they'll pave the way for more sophisticated probes that could enter orbit around other stars or even land on other worlds. As we develop this technology, we'll need to think carefully about the implications. Every probe we send to another star system is an ambassador for humanity, carrying information about our civilization to any intelligence that might discover it. The Voyager spacecraft carry golden records with sounds and images from Earth. But future probes could carry far more, perhaps the entirety of human knowledge encoded in crystalline memory, waiting to be discovered by alien archaeologists millions of years from now. The possibility that 3I Atlas was carrying such information adds another layer to its mystery. Even if it was a natural comet, it carried information about its home star system in its chemical composition and physical structure. But if it was artificial, it might have been carrying deliberate messages, encyclopedia of alien knowledge, or even preserved biological samples. The fragments that survive their passage through our solar system and return to interstellar space might be carrying information about us as well, adding our chapter to whatever cosmic story they're telling. As we drift deeper into contemplation of these cosmic possibilities, the boundaries between science and philosophy, between observation and imagination, begin to blur. The fragmentation of 3I Atlas was a real event, observed by telescopes and recorded in data. But its meaning, its implications, its place in the larger story of cosmic intelligence, these are questions that science alone cannot answer. They require us to think beyond the immediate data, to imagine possibilities that might not be testable for decades or centuries, to consider our place in a universe that might be teeming with intelligence we're only beginning to perceive. The night sky, which has inspired wonder for as long as humans have looked upward, takes on new meaning when we consider the possibility of von Neumann probes and interstellar messengers. Those points of light aren't just distant suns, but potential homes to other civilizations, other intelligences contemplating the same questions we are. And travelling between those stars, invisible to our eyes but increasingly visible to our instruments, might be the probes, the messengers, the fragments of cosmic ambition launched by species we've never met, but with whom we share the fundamental drive to explore, to understand, to connect across the vast darkness. As we prepare to explore the concept of Three-Eye Atlas as a potential cosmic dandelion, spreading seeds or sensors throughout our solar system, we're venturing even deeper into the realm of possibility. The image is poetic, a celestial object releasing its payload like a dandelion, releasing its seeds on the wind, but it's also scientifically intriguing. Nature has evolved numerous strategies for dispersal and propagation, and an advanced civilization might have learned from these natural examples, creating technology that mimics biology on a cosmic scale. The universe has always been generous with its mysteries, providing just enough answers to keep us searching while maintaining enough secrets to keep us wondering. The fragmentation of Three-Eye Atlas was one such gift, a cosmic event that answered some questions while raising many more. Whether it was a natural comet breaking apart under thermal stress or something far more extraordinary, it has expanded our conception of what's possible and reminded us that the universe is far stranger and more wonderful than we often imagine. The concept of panspermia, the idea that life can spread between planets and even between star systems, has been seriously discussed in scientific circles for over a century. But traditionally, this has been imagined as a passive process, with microorganisms hitching rides on asteroids and comets, surviving the journey through space by chance rather than design. What if we've been thinking too small? What if panspermia could be directed, intentional, engineered? What if advanced civilizations have been seeding the galaxy with life for billions of years, using comets and asteroids as their delivery vehicles? This is where the image of Three-Eye Atlas as a cosmic dandelion becomes particularly compelling. Just as a dandelion releases hundreds of seeds, each carried on its own tiny parachute to find new ground to colonize, Three-Eye Atlas released dozens of fragments, each potentially carrying its own cargo to different parts of our solar system. If this was engineered, it represents a dispersal strategy of elegant simplicity. No need for complex navigation or propulsion systems for each seed. Just release them at the right point and let orbital mechanics and solar radiation pressure carry them to their destinations. The seeds themselves could be incredibly small, perhaps microscopic. We're already developing technology that can pack enormous complexity into tiny packages. A single bacterium contains all the information needed to replicate itself, to metabolize resources, to respond to its environment. It's a natural nanomachine of extraordinary sophistication. An advanced civilization might be able to create artificial seeds with similar or greater capabilities. Tiny probes able to analyze their environment, gather resources, replicate if conditions are suitable, or remain dormant if they're not. Consider what such seeds might do upon reaching different destinations in our solar system. Those that fell toward the sun would be destroyed, but not before potentially analyzing the solar wind and magnetic field, transmitting data back to their siblings or to some distant receiver. Seeds reaching Earth might analyze our atmosphere, detecting the unmistakable signatures of life, oxygen, methane, and other gases that shouldn't coexist in chemical equilibrium. They might even sample our biosphere, learning about Earth's biology at a molecular level. Seeds reaching Mars could search for signs of past or present life, analyzing the subsurface for organic molecules or metabolic signatures. Those landing on Europa or Enceladus could attempt to penetrate the ice and explore the hidden oceans beneath, looking for the warm chemical environments where life might thrive. Seeds reaching the asteroid belt could analyze the composition of these ancient bodies, learning about the formation and evolution of our solar system. The beauty of this strategy is its redundancy and adaptability. Even if most seeds are destroyed or land in unsuitable locations, some will find interesting targets. And because each seed can be programmed with sophisticated decision-making capabilities, they can adapt their behavior based on what they find. A seed landing on a lifeless rock might simply record basic geological data and shut down. But a seed detecting signs of life might activate more sophisticated instruments, perhaps even attempting to communicate with any intelligence it detects. This brings us to a fascinating possibility. What if some of the fragments of 3i Atlas are still active in our solar system? They could be so small that we haven't detected them, perhaps orbiting Earth or other planets, quietly observing and recording. They might be on the surface of the Moon, Mars, or asteroids, powered by solar energy or radioactive decay, patiently gathering data. They could even be in Earth's atmosphere or oceans, microscopic observers studying our biosphere from within. The technology to detect such tiny probes doesn't really exist yet, but it's not beyond imagination. As we develop better instruments for detecting and tracking small objects in space, for analyzing atmospheric particles, for studying microscopic samples from other worlds, we might discover anomalies that don't fit our expectations. A particle with an unusual isotopic signature, a microscopic structure that seems too regular to be natural, a pattern of observations that suggests intentional monitoring rather than random sampling. The implications of discovering such seeds would be profound. It would mean that our solar system, and by extension Earth itself, is under observation by an intelligence that might be millions of years old. It would mean that information about our world, our biosphere, possibly even our civilization, is being collected and potentially transmitted to unknown recipients. It would transform our understanding of privacy and sovereignty on a cosmic scale. But it would also mean that we're not alone, that someone or something cared enough to send probes across the vast distances between stars to learn about our world. It would be a form of contact, albeit indirect and possibly unidirectional. The seeds might not be capable of complex communication, but their very existence would be a message. You are known, you're observed, you're part of a larger community. The timing of 3i Atlas's fragmentation continues to intrigue when considered from this perspective. The comet began breaking apart just as it entered the region of our solar system where planets orbit. If the fragmentation was triggered by proximity to planets, rather than just solar heating, it would suggest a sophisticated detection and response system. The seeds could have been released specifically because the probe detected interesting targets, worlds worth investigating more closely. Our own plans for exploring other star systems include similar strategies. The Breakthrough Starshot project envisions sending thousands of tiny probes to Proxima Centauri, knowing that many will be lost, but hoping that some will successfully transmit data back to Earth. Each probe would be little more than a computer chip with a light sail, but thousands of them would provide redundancy and the ability to explore multiple targets. It's not hard to imagine a more advanced version of this concept, with probes capable of more sophisticated observations and even sample collection. The biological analogies go even deeper. Many organisms on Earth use dispersal strategies that seem almost designed for space travel. Tardigrades, also known as water bears, can survive extreme conditions including the vacuum of space, radiation levels that would kill most life, and temperatures near absolute zero. Some bacteria form endospores that can remain dormant for millions of years, waiting for suitable conditions to revive. These natural examples of extreme survival might inspire or inform the design of interstellar seeds. What if the seeds released by 3i Atlas weren't purely technological, but incorporated biological elements? They could be hybrid devices, combining the durability and computational power of technology with the adaptability and self-replication capabilities of biology. Such biotechnological seeds could potentially establish themselves in suitable environments, creating observation posts that grow and evolve over time. It sounds like science fiction, but we're already experimenting with biological computers, organic electronics, and hybrid biomechanical systems. The ethical implications of seeding other star systems with life or technology are complex and profound. Do we have the right to potentially contaminate other worlds with Earth life? What if those worlds already harbour their own life that could be disrupted or destroyed by introduced organisms? These are questions we're already grappling with as we send rovers to Mars and plan missions to Europa and Enceladus. but they become even more complex when considering interstellar distances and timescales. An advanced civilization that has been sending out seeds for millions of years might have developed sophisticated ethical frameworks for such activities. Perhaps the seeds are programmed to detect existing life and avoid interference. Perhaps they only activate in sterile environments where they won't disrupt existing ecosystems. Or perhaps, from a cosmic perspective that spans millions of years and thousands of star systems, the spreading of life is seen as a fundamental good that outweighs the risks of contamination. The fragmentation pattern of 3I Atlas showed interesting regularities that could support the engineered dispersal hypothesis. The fragments weren't randomly sized but seemed to cluster around certain dimensions. This could be natural, the result of pre-existing fracture planes in the comet's nucleus. But it could also be designed, with each fragment sized appropriately for its intended mission. Larger fragments might carry more sophisticated instruments or serve as communication relays. Smaller fragments might be simple sensors designed to take basic measurements and transmit minimal data. The velocities at which the fragments separated were also intriguing. They were moving apart slowly, at speeds of just a few meters per second relative to each other. This gentle separation would allow the fragments to gradually spread throughout the inner solar system without requiring excessive energy. If you were designing a dispersal mechanism, this is exactly the kind of low-energy, efficient approach you might choose. As we observe the fragments evolving over time, some brightening and others fading, we might have been watching different types of seeds activating or deactivating based on their programming and environment. Bright fragments might have been those with active sensors or communication systems. Dark fragments might have been those in dormant mode, conserving energy until they reach their target destinations. The variety we observed could represent a sophisticated multi-mission architecture rather than random variation. The chemical composition of the fragments, as revealed by spectroscopy, showed both similarities and differences compared to solar system comets. The similarities could be intentional camouflage, making the probe appear natural to casual observation. The differences could be functional, representing materials needed for the probe's mission that wouldn't naturally occur in comets. Unfortunately, our observations weren't detailed enough to definitively identify artificial materials, but future interstellar visitors might provide better opportunities for such analysis. One of the most intriguing aspects of the cosmic dandelion hypothesis is the possibility of communication between seeds. If the fragments of 3I Atlas were technological seeds, they might have been designed to work together, sharing information and coordinating their observations. This would create a distributed sensor network throughout our solar system, able to monitor multiple phenomena simultaneously and correlate observations from different vantage points. Such a network would be incredibly valuable for understanding a star system comprehensively. By having sensors at different distances from the Sun, you could study how the solar wind varies with distance. By having sensors near different planets, you could compare atmospheric compositions and search for biosignatures. By having sensors in different orbital planes, you could map the three-dimensional structure of the solar system's magnetic field and dust distribution. We actually use similar distributed sensor networks for studying Earth. Weather satellites, ocean buoys, seismic stations, and atmospheric monitoring equipment all work together to give us a comprehensive picture of our planet's systems. An interstellar probe using the cosmic dandelion strategy would be applying the same principle on a solar system scale, creating an observation network that no single probe could achieve. The communication between seeds wouldn't need to be obvious or easy to detect. They might use highly directional transmissions that we'd only notice if we happen to be in the beam path. They might communicate using exotic methods we haven't discovered yet, quantum entanglement, neutrino beams, or modulated gravitational waves. Or they might not communicate at all during their observation phase, instead storing data for later retrieval or transmission when their mission is complete. As we contemplate these possibilities, it's worth considering what evidence we should look for to test the cosmic dandelion hypothesis. First, we should carefully analyze the trajectories of all fragments from future interstellar visitors, looking for patterns that might indicate intentional targeting rather than random dispersal. Second, we should search for anomalous objects in our solar system that might be dormant seeds from previous interstellar visitors. Third, we should develop detection methods for microscopic probes, perhaps by looking for unusual isotopic ratios or artificial structures in collected samples. The search for cosmic seeds would require new approaches and technologies. We'd need to think like detectives, looking for clues that might be subtle or hidden. An artificial seed might be designed to look natural under casual observation, but reveal its true nature only under specific conditions or detailed analysis. We might need to examine meteorites more carefully, analyze atmospheric particles more thoroughly, and study the surfaces of asteroids and moons with greater precision. The possibility that Earth has been receiving cosmic seeds for billions of years adds another dimension to the mystery of life's origin. Perhaps life didn't begin on Earth at all, but was seeded here by an ancient probe that passed through our solar system when Earth was young. The building blocks of life, or even life itself, could have been delivered intentionally rather than by chance. This directed panspermia hypothesis has been seriously proposed by scientists including Francis Crick, co-discoverer of DNA's structure. If true, it would mean that life on Earth is part of a vast galactic ecosystem, connected to life on other worlds through the patient work of cosmic gardeners. The seeds that grew into Earth's biosphere might have siblings that grew into different forms of life on other worlds, adapted to different conditions but sharing a common origin. We might have cosmic cousins we've never met, other biospheres that arose from the same dispersal event that seeded Earth. The fragmentation of 3I Atlas could represent a modern example of this ancient process. Even if the comet was natural, it might have been carrying organic molecules or even dormant microorganisms from its home star system. As it fragmented, these biological passengers would have been dispersed throughout our solar system. Most would be destroyed by radiation or heat, but some might survive, especially if they landed in protected environments like the subsurface of Mars or the interiors of asteroids. Future missions to collect samples from asteroids, comets, and other worlds should be designed with the possibility of cosmic seeds in mind. We should look not just for indigenous life, but for life or technology that might have arrived from elsewhere. The discovery of clearly non-terrestrial biology, or obviously artificial structures, would revolutionize our understanding of our place in the universe. As our night journey continues, we find ourselves at the intersection of science and imagination, observation and speculation. The fragmentation of 3I Atlas was a real event, but its interpretation remains open. Was it a natural comet breaking apart under thermal stress? Was it a von Neumann probe deploying its exploratory systems? Was it a cosmic dandelion releasing its seeds into our solar system? We don't know, and perhaps we never will know for certain, but the very act of considering these possibilities expands our consciousness and prepares us for whatever discoveries await. By thinking seriously about cosmic seeds and interstellar probes, we're developing the conceptual framework we'll need if we ever do discover evidence of extraterrestrial intelligence. We're training ourselves to see the universe not as a collection of isolated star systems, but as an interconnected web of matter, energy, and possibly life and intelligence. The seeds released by 3I Atlas, whether natural or artificial, have completed their initial dispersal. Some have already met their end in the sun's fierce heat. Others continue their journey through our solar system, carrying their secrets with them, and perhaps some have found their targets, settling onto worlds or into orbits where they can complete whatever mission they were designed for, or where they can contribute their materials to the cosmic cycles of chemistry and potentially biology. As we drift deeper into sleep, carried along by these cosmic currents of possibility, we're approaching perhaps the most profound aspect of our journey, the question of what it all means for humanity's future and our understanding of our place in the cosmos. The search for signals from other civilizations, the patient listening for whispers across the vast darkness, takes on new dimensions when we consider that the messages might not be electromagnetic but physical, not broadcasts but artifacts, not signals but seeds. The search for whispers in the cosmic static represents one of humanity's most profound endeavours, a quest that speaks to our deepest questions about existence and our place in the universe. For decades now, we've been pointing our most sensitive instruments toward the stars, listening for signals that might indicate we're not alone. Radio telescopes scan millions of frequencies, optical telescopes search for laser pulses, and sophisticated computer algorithms sift through the noise looking for patterns that nature alone couldn't create. But what if we've been listening for the wrong kind of whispers? What if the messages aren't electromagnetic at all, but physical, carried not on waves of light, but in the fragments of objects like 3 Atlas? The history of SETI, the search for extraterrestrial intelligence, is a story of expanding imagination and evolving technology. When Frank Drake first pointed a radio telescope at nearby stars in 1960, he was operating on the assumption that alien civilizations would communicate using radio waves, just as we had recently learned to do. It seemed logical. Radio waves travel at the speed of light, they can carry complex information, and they propagate through space relatively unimpeded. But 60 years of listening has yielded no confirmed signals, no alien broadcasts, no cosmic hellos. This silence has forced us to reconsider our assumptions about how advanced civilizations might communicate or reveal their presence. The traditional SETI approach assumes that alien civilizations would want to communicate, that they would deliberately broadcast signals for others to detect. But what if that assumption is wrong? What if advanced civilizations have learned that broadcasting your presence to the cosmos is dangerous, attracting unwanted attention from hostile forces? Or what if they've simply moved beyond electromagnetic communication, finding it too slow, too prone to interference, too primitive for their needs? The fragmentation of 3i Atlas suggests another possibility, that messages might be encoded in physical objects, in the trajectories of fragments, in the chemical compositions of cosmic visitors. Consider the advantages of physical messaging over electromagnetic signals. A radio broadcast spreads out as it travels, becoming weaker with distance according to the inverse square law. By the time a signal from a nearby star reaches Earth, it's incredibly faint, easily lost in the cosmic noise. But a physical object maintains its integrity as it travels. A probe or seed that left another star system millions of years ago arrives at our solar system with all its information intact, its message preserved in its structure, its composition, its behavior. Physical objects can also carry far more information than electromagnetic signals. A single interstellar probe could contain the entire knowledge base of a civilization, encoded in crystalline memory, or even in the arrangement of atoms in specially designed molecules. The fragments of 3i Atlas, if they were artificial, could each be carrying terabytes or even exabytes of information, waiting to be decoded by a civilization sophisticated enough to read them. We might have watched a cosmic library dispersing through our solar system, each fragment a volume in an encyclopedia we don't yet know how to read. The search for these physical messages requires different techniques than traditional SETI. Instead of listening for radio signals, we need to watch for unusual objects, strange trajectories, or unexpected behaviors. The Pan-STARRS telescope that discovered Oumuamua, the Atlas system that found 3i Atlas, and other sky surveys are inadvertently conducting a new kind of SETI, one that looks for artifacts rather than signals. Every unusual asteroid, every interstellar visitor, every object that doesn't quite fit our expectations could potentially be a message or messenger from another civilization. The challenge is distinguishing artificial objects from natural ones, especially when advanced technology might be designed to mimic nature. An alien probe disguised as an asteroid would be nearly impossible to identify without close examination. Even the fragmentation of 3i Atlas, as unusual as it was, falls within the range of natural possibilities. We need to develop new criteria, new observational techniques, and new analytical methods to identify potential artifacts among the countless natural objects in our solar system. One approach is to look for statistical anomalies. If alien probes are regularly passing through our solar system, they might create subtle patterns in the distribution of objects we observe. Perhaps certain orbital parameters are favored, certain compositions are overrepresented, or certain behaviors occur more frequently than natural processes would predict. The fragmentation of 3i Atlas at a specific distance from the Sun, if repeated by future interstellar visitors, might indicate a programmed response rather than a natural phenomenon. Another approach is to search for technosignatures, evidence of technology that couldn't be produced by natural processes. This might include unusual isotope ratios that indicate nuclear processing, materials or structures that require advanced manufacturing, or behaviors that suggest active guidance or control. The unexplained acceleration of Oumuamua, the unusual fragmentation of 3i Atlas, and other anomalies might be subtle technosignatures we're just beginning to recognize. The search for physical messages also extends to our own solar system. If alien probes have been visiting our solar system for millions or billions of years, some of them might still be here. They could be orbiting the Sun in unusual orbits, hiding among the asteroids, or sitting dormant on the Moon or other airless bodies where they could survive for eons. The lunar surface, undisturbed by weather or geological activity, would be an ideal place for an alien artifact to wait for discovery. Future lunar missions should include searches for anomalous objects that might be of artificial origin. The possibility of finding an alien artifact on the Moon might sound like science fiction, but it's been seriously proposed by scientists. The Moon's surface preserves impact craters billions of years old, and any artifact placed there could survive almost indefinitely. If an alien probe wanted to leave a message for future civilizations that might arise on Earth, the Moon would be a perfect billboard, visible from Earth, accessible once we developed spaceflight, and protected from the erosion that would destroy artifacts on Earth's surface. The fragments of 3i Atlas that survived their passage through our solar system might have left similar calling cards. Some fragments could have impacted the Moon, Mars, or asteroids, leaving traces we might discover in future missions. Others might have entered stable orbits where they could be recovered and studied. The challenge is finding these tiny needles in the vast haystack of our solar system, but as our survey capabilities improve, we might discover that some of the objects we've been observing for years are not what they seem. The electromagnetic search for extraterrestrial intelligence hasn't been abandoned, but it's being reconsidered in light of new possibilities. Perhaps alien civilizations do use radio or optical communications, but in ways we haven't anticipated. They might use spread spectrum techniques that make their signals look like noise. They might communicate using quantum entanglement or other exotic physics we haven't discovered. Or they might use electromagnetic signals only for local communication, relying on physical probes for interstellar messaging. The Breakthrough Listen project, the most comprehensive SETI search ever undertaken, is expanding its scope to include searches for artifacts and unusual objects. Using machine learning algorithms to analyze vast amounts of data, the project is looking for patterns that human observers might miss. Every piece of data is examined for anomalies, whether electromagnetic or physical, that might indicate the presence of extraterrestrial intelligence. The fragmentation of 3i Atlas has been added to the database of interesting events that might represent attempts at communication or contact. The idea that we should look for physical artifacts rather than electromagnetic signals represents a fundamental shift in SETI philosophy. Instead of assuming that aliens want to communicate with us, we're considering the possibility that they might be studying us, that their primary goal might be observation rather than communication. The fragments of 3i Atlas could have been sensors, quietly gathering data about our solar system and transmitting it back to their creators by means we can't detect. This observational approach to interstellar exploration makes sense from many perspectives. A civilization wanting to study the galaxy comprehensively would need to observe many star systems over long periods. Sending probes that can operate autonomously for millions of years would be more practical than trying to maintain active communication with thousands or millions of distant sensors. The probes could be programmed to observe quietly, recording data about planets, stars, and any life or intelligence they encounter, storing this information for eventual retrieval or transmission. The timing of observations becomes crucial in this scenario. A probe that arrived at Earth 1 million years ago would have seen a very different planet than exists today. There would have been no signs of technology, no radio emissions, no artificial lights visible from space. The probe might have catalogued Earth as a living world, but not one requiring immediate attention. But if probes are regularly passing through our solar system, if the galaxy is full of patient observers, then our recent technological development might have triggered increased interest. The fragmentation of 3i Atlas occurred just as humanity was reaching a technological threshold. We had recently developed the ability to detect interstellar objects, to analyze their composition spectroscopically, to track their trajectories precisely. If the fragmentation was triggered by our technological development rather than by solar heating, it would represent a form of responsive observation, the probe recognizing that the system it was studying had developed a technological civilization and adjusting its mission accordingly. This possibility leads to profound questions about surveillance and privacy on a cosmic scale. If our solar system is under observation by alien probes, what are they learning about us? Our radio and television broadcasts have been leaking into space for decades, creating an expanding bubble of information about human civilization. Any probe within 100 light-years could potentially detect and decode these signals, learning about our history, our cultures, our conflicts, and our dreams. The fragments of 3 Atlas, if they were sensors, might have been collecting more subtle information, the chemical composition of our atmosphere, the spectrum of our city lights, the electromagnetic signatures of our technology. The ethical implications of cosmic surveillance are complex. From one perspective, it might seem like a violation of privacy, an uninvited intrusion into our solar system, but from another perspective, it might be seen as a natural part of living in a galaxy where intelligence has emerged multiple times. Just as we study other star systems with our telescopes, other civilizations might study ours with their probes. It's a form of mutual observation that could eventually lead to communication and contact when both parties are ready. The search for whispers in the static has taught us patience. We've been actively searching for extraterrestrial intelligence for only about 60 years, less than a human lifetime. In cosmic terms, this is barely an instant. The galaxy is 13 billion years old, and civilizations might rise and fall on timescales of millions of years. The chances of detecting a signal or artifact during our brief search might be small, but they're not zero. Every unusual object like 3i Atlas, every anomalous observation, every unexplained phenomenon could be the whisper we've been waiting to hear. The fragmentation of 3i Atlas might have been one such whisper, too faint for us to properly understand with our current technology and knowledge. But as we develop better instruments, as we accumulate more observations, as we refine our understanding of what to look for, we might recognize patterns we're currently missing. The whispers might be there in the data we've already collected, waiting for us to learn how to hear them. The development of artificial intelligence and machine learning is revolutionizing our ability to search for these whispers. AI systems can analyze vast amounts of data, looking for patterns too subtle for human observers to notice. They can compare observations across different wavelengths, different times, different locations, finding correlations that might indicate artificial origin. The behavior of 3i Atlas and its fragments is being analyzed by these systems, searching for any signs that might distinguish it from natural comets. But perhaps the most important aspect of searching for whispers in the static is what it teaches us about ourselves. The very act of searching, of wondering whether we're alone, of imagining what other intelligences might be like, expands our consciousness and deepens our understanding of our place in the universe. Whether or not we ever detect alien signals or artifacts, the search itself is transforming us. making us more aware of our cosmic context, more thoughtful about our future, more united in our shared curiosity about the universe. The fragments of 3i Atlas have dispersed now, some destroyed, others continuing their journeys through space. But the questions they raised remain, echoing in the minds of scientists and dreamers alike. Were they natural fragments of a comet, or were they something more? Were they carrying messages we couldn't read, or performing observations we couldn't detect? Were they whispers in the cosmic static that we heard but didn't understand? These questions may never be definitively answered, but they've become part of the great conversation humanity is having with the cosmos. As we continue to listen and watch, to search for whispers in the static and artifacts in the void, we're preparing ourselves for whatever discoveries await. The next interstellar visitor might be more obviously artificial, or it might provide the key to understanding previous visitors like 3i Atlas. Each observation adds to our knowledge, each anomaly expands our imagination, each whisper brings us closer to answering the ultimate question: are we alone? The patience required for this search is almost incomprehensible by human standards. We might need to listen and watch for centuries or millennia before we detect unambiguous evidence of extraterrestrial intelligence. But the search itself is valuable, driving technological development, inspiring scientific research, and uniting humanity in a common quest. The fragments of 3i Atlas reminded us that the universe is full of surprises, that messengers from other stars do pass through our solar system, and that we have the capability to detect and study them. The static we're searching through isn't really static at all. It's the combined voices of the cosmos, the electromagnetic and physical emissions of billions of stars, planets, and possibly civilizations. Somewhere in that cosmic chorus might be deliberate messages, intentional signals, or artificial artifacts waiting to be discovered. The fragmentation of 3i Atlas might have been one note in this vast symphony, a whisper we're just beginning to learn how to hear. As our technology improves, as our understanding deepens, as our patience extends, we're becoming better listeners, more perceptive observers, more sophisticated interpreters of cosmic phenomena. The whispers are out there, carried on radio waves, encoded in laser pulses, or embedded in the trajectories and compositions of interstellar visitors. We just need to keep listening, keep watching, keep wondering, and eventually, perhaps, we'll hear the clear voice of another intelligence calling across the cosmic darkness. The Great Silence, as it's sometimes called, is one of the most profound mysteries in science. If the universe is billions of years old, if there are hundreds of billions of stars in our galaxy alone, if planets are common and life arose relatively quickly on Earth, then where is everybody? This is the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" during a lunch conversation about flying saucers. The fragmentation of 3i Atlas offers us a new lens through which to examine this ancient question, suggesting that perhaps the silence isn't as complete as we thought, that perhaps the universe is speaking to us in languages we're just beginning to learn. The traditional formulation of the Fermi paradox assumes that advanced civilizations would be obvious, that they would have colonized the galaxy, built megastructures we could detect, or at least sent signals we could receive. But what if these assumptions are wrong? What if advanced civilizations are subtle rather than obvious, patient rather than expansive, observant rather than communicative? The fragmentation of 3i Atlas might represent exactly this kind of subtle presence. A gentle investigation rather than a dramatic announcement, a whisper rather than a shout. Consider the possibility that the Great Silence is actually filled with gentle answers, with quiet messages we haven't learned to perceive. Every interstellar object that passes through our solar system could be carrying information from other civilizations. Every unusual asteroid could be a dormant probe. Every unexplained astronomical phenomenon could be evidence of intelligence at work. We've been looking for loud, obvious signals when perhaps the cosmos communicates in subtler ways, through physical messengers like 3i Atlas that require patience and sophistication to understand. The fragmentation pattern of 3i Atlas offers an interesting perspective on how civilizations might choose to reveal themselves. Instead of a dramatic arrival, a clear announcement of "we are here," the comet broke apart gradually, gently, in a way that could be interpreted as either natural or artificial. This ambiguity might be intentional. An advanced civilization might want to observe how we respond to ambiguous signals, whether we're curious or fearful, whether we're ready for contact or would panic at clear evidence of alien intelligence. This gentle approach to contact makes sense from multiple perspectives. A civilization that has survived for millions of years has likely learned patience. They would understand that forcing contact on an unprepared species could be harmful, could disrupt natural cultural evolution, could cause panic or conflict. By sending ambiguous messengers like 3i Atlas, they could gauge our readiness, our scientific sophistication, our psychological preparedness for learning we're not alone. The fragments spreading through our solar system could be tests as much as observations, seeing how we respond, what we investigate, what conclusions we draw. The Great Silence might also be a result of the vast timescales involved in galactic evolution. Civilizations might rise and fall on timescales of millions of years, with periods of expansion followed by periods of contraction or transcendence. At any given moment, there might be only a few active, communicating civilizations in the galaxy. The rest might be extinct, dormant, or evolved beyond our ability to recognize them. The fragments of 3i Atlas could be relics from a civilization that no longer exists in its original form, automated messengers continuing their mission long after their creators have disappeared or transformed. There's also the possibility that the Great Silence is maintained deliberately, that there's a galactic consensus to avoid interfering with developing civilizations. This prime directive hypothesis suggests that advanced civilizations might have agreed to observe but not contact younger species until they reach certain milestones. The fragmentation of 3i Atlas could have been triggered by our reaching one of these milestones, perhaps the development of space technology, or the ability to detect interstellar objects or some other threshold we're not even aware of. The timing of our technological development relative to the age of the galaxy adds another dimension to the paradox. We've only been a technological civilization for about a century, a mere instant in cosmic time. If civilizations typically take billions of years to develop technology, we might be among the first in our galaxy. The interstellar objects we're seeing might be natural after all, with artificial messengers still to come as other civilizations develop and begin their own exploration programs. Or perhaps we're late to the party, and the galaxy has already been thoroughly explored, with probes like 3 Atlas being routine surveys checking on the development of new civilizations. The possibility that 3 Atlas was a gentle answer to the Fermi paradox, a subtle "we are here" message, changes how we think about searching for extraterrestrial intelligence. Instead of looking only for obvious techno-signatures, we should be alert to subtle anomalies, to patterns that don't quite fit natural explanations, to objects and phenomena that seem designed to test our observational and analytical capabilities. The fragmentation might have been a puzzle deliberately presented to us, seeing if we're sophisticated enough to recognize it as potentially artificial. The distribution of the fragments through our solar system could be seen as an invitation to explore, to develop our space capabilities to investigate these cosmic messengers more closely. Some fragments headed toward Mars, others toward the asteroid belt, still others back to interstellar space. If we want to study them, we need to develop better spacecraft, more sophisticated instruments, more ambitious space programs. In this way, the fragments could be encouraging our technological development, providing goals that stretch our capabilities without overwhelming us. The chemical composition of the fragments, similar to but subtly different from solar system comets, might be another gentle hint. It tells us that the object came from elsewhere, that other star systems exist with slightly different conditions, that the galaxy is diverse and interesting. but it's not so different as to be shocking or incomprehensible. It's as if the message is, we're different, but not too different. We're from another star, but we're part of the same galaxy. We're alien, but we're made of the same basic stuff you are. This gentle approach to answering the Fermi paradox might be common throughout the galaxy. Instead of dramatic first contacts, civilizations might prefer subtle introductions, gradual revelations, patient development of relationships across vast distances and timescales. The fragments of 3i Atlas could be part of a slow conversation that takes place over centuries or millennia, with each interstellar visitor adding another piece to the puzzle, another hint about the nature of our cosmic neighbors. The great silence might also be more apparent than real because we're listening for the wrong things in the wrong ways. Our searches for extraterrestrial intelligence have focused on radio and optical signals. But what if advanced civilizations communicate using neutrinos, gravitational waves, or some physics we haven't discovered yet? What if they encode messages in the cosmic microwave background, in the distribution of dark matter, in the patterns of stellar motion? The fragmentation of 3i Atlas might have been accompanied by signals we couldn't detect, messages we couldn't receive with our current technology. There's also the sobering possibility that the Great Silence reflects a genuine absence, that life is extraordinarily rare, that intelligence is even rarer, and that technological civilizations capable of interstellar communication or travel are so uncommon that we might be the only one in our galaxy at this time. In this scenario, 3i Atlas was just a natural comet, its fragmentation a result of ordinary physics, its interstellar origin a reminder of the galaxy's natural processes rather than its intelligent inhabitants. This would make us extraordinarily precious, the only known consciousness in a vast unconscious cosmos. But even if we are alone, the search for others has value. It drives us to develop better technology, to think more deeply about our place in the universe, to consider our responsibilities as possibly the only intelligence in the galaxy. The fragmentation of 3i Atlas, whether natural or artificial, reminded us that we're part of a larger cosmic story, that material and potentially information flows between star systems, that we're connected to the rest of the galaxy even if we're its only conscious observers. The psychological impact of the Great Silence on humanity is profound. It can lead to feelings of cosmic loneliness, of existential isolation, of being a single point of consciousness in a vast and different universe. But it can also inspire a sense of cosmic responsibility, of being the universe's way of understanding itself, of having a unique role in bringing consciousness and purpose to an otherwise unconscious cosmos. The ambiguous nature of objects like 3i Atlas allows us to maintain hope while accepting uncertainty, to continue searching while living with the possibility that we might be alone. As we've observed more interstellar objects, patterns are beginning to emerge that might help resolve the Fermi paradox. Each object, Oumuamua, Borisov, 3i Atlas, has been different, suggesting a diversity of objects traveling between stars. This diversity might indicate multiple sources, multiple formation mechanisms, or possibly multiple types of probes from different civilizations. As our sample size grows, we might be able to distinguish between natural and artificial origins, between random visitors and deliberate messengers. The rate at which we're discovering interstellar objects is itself informative. If we found 3 in just a few years of looking, there must be millions passing through our solar system over geological time. This abundance suggests that interstellar space is full of objects traveling between stars, creating a natural transportation network that life or intelligence could exploit. The fragmentation of 3i Atlas demonstrated one way this network might function, with single objects splitting into multiple messengers to explore different targets. The Great Silence might be ending, not with a dramatic signal or obvious contact, but with a gradual accumulation of subtle evidence. Each interstellar visitor teaches us something new, expands our perspective, challenges our assumptions. The fragments of 3i Atlas spreading through our solar system might be part of this gentle revelation, this slow introduction to our cosmic context. We might look back on this period as the time when the silence began to break, when the whispers became audible, when we started to realize we're not as alone as we thought. The philosophical implications of the Great Silence and its potential resolution through objects like 3i Atlas are staggering. If we're alone, we bear the responsibility of being the only known consciousness in the galaxy, the only beings capable of appreciating beauty, understanding science, creating art, feeling love. If we're not alone, we're part of a cosmic community we're just beginning to discover, with all the opportunities and challenges that implies. Either way, the fragmentation of 3i Atlas reminded us that we're participants in a cosmic story much larger than ourselves. The patience required to resolve the Fermi paradox might span generations or even millennia. We might need to observe hundreds or thousands of interstellar objects before patterns become clear, before we can distinguish natural from artificial, before we can decode any messages they might carry. The fragments of 3i Atlas that survived and continued into interstellar space might be recovered by future generations with better technology, finally revealing whether they were natural or artificial. Our descendants might look back on us as the generation that first noticed these cosmic messengers but lacked the tools to fully understand them. The search for answers to the Great Silence is transforming our civilization. It's driving technological development, inspiring scientific research, promoting international cooperation, and expanding our philosophical horizons. Whether 3i Atlas was a natural comet or an artificial probe, its fragmentation was a reminder that the universe is dynamic, surprising, and full of mysteries waiting to be solved. The Great Silence might not be silent at all, we might just be learning how to listen. As we approach the end of our cosmic journey, contemplating what it means to find our harbour of home in this vast universe, the fragmentation of 3i Atlas takes on a deeply personal dimension. We've travelled far in our imagination tonight, from the moment this interstellar visitor began breaking apart in our solar system to contemplating the grandest questions about intelligence, communication, and our place in the cosmos. But now it's time to bring our attention back to Earth, to our small, beautiful world orbiting an ordinary star in an unremarkable corner of the galaxy. Because in the end, all cosmic mysteries, all universal questions, all searches for meaning ultimately bring us back to the fundamental question of what it means to be human, to be conscious, to be home in a universe that might or might not contain other intelligences. The fragments of 3i Atlas that fell toward the sun are gone now, vaporized in our star's fierce heat. Their atoms joining the solar wind to be scattered throughout the solar system. Some of those atoms will eventually fall to Earth, becoming part of our atmosphere, our oceans, perhaps even our bodies. In this way, 3 Atlas has become part of our world, part of us. We are already cosmic beings, made of star stuff, as Carl Sagan reminded us, and now we carry within us atoms from another star system, brought here by an interstellar messenger whose true nature we may never fully understand. This physical connection to the cosmos through objects like 3i Atlas reminds us that Earth is not separate from the universe but deeply embedded within it. Our harbour of home is not isolated but connected to every other star system through the patient wandering of comets and asteroids, through the gentle rain of cosmic dust, through the electromagnetic radiation that bathes our planet from distant suns. Every breath we take contains atoms that have travelled between stars. Every glass of water we drink contains molecules that might have formed in interstellar space. We are not just in the universe is in us. The search for meaning in the fragmentation of 3i Atlas ultimately brings us back to the search for meaning in our own existence. Whether the comet was natural or artificial, whether we're alone or part of a cosmic community, we still face the same fundamental questions that humans have always faced. What is our purpose? How should we live? What legacy will we leave? The cosmic perspective provided by interstellar visitors like 3i Atlas doesn't answer these questions, but it does provide a framework for thinking about them, on a scale that transcends our individual lives, our cultures, even our species. If 3i Atlas was a natural object, its fragmentation reminds us of the beauty and complexity of natural processes. The universe doesn't need intelligence to create wonder. The simple physics of ice sublimating in sunlight, of gravity pulling fragments apart, of chemistry playing out on a cosmic scale, these natural processes create phenomena of breathtaking beauty and complexity. Our harbour of home exists within this natural splendour, and we're privileged to be conscious observers of it, able to appreciate and understand the cosmic forces that shaped us and continue to shape our world. If 3's Atlas was artificial, its fragmentation suggests that we're not alone in appreciating this cosmic beauty, that other intelligences have looked up at their night skies with the same wonder we feel, have asked the same questions we ask, have sent their own messengers across the vast darkness seeking connection and understanding. Our harbour of home would then be one of many harbours in a galaxy full of consciousness, each unique but all sharing the fundamental experience of being aware in a vast cosmos. The timing of 3i Atlas's visit, during this particular moment in human history, feels significant regardless of the comet's nature. We're living through an extraordinary period of discovery and transformation. We've detected gravitational waves, confirming Einstein's century-old prediction. We've discovered thousands of planets orbiting other stars, many of them potentially habitable. We've begun to understand dark matter and dark energy, the invisible components that make up most of the universe. And now we're detecting and studying visitors from other star systems, physical messengers that connect us to the broader galaxy. This convergence of discoveries is transforming our understanding of our harbour of home. Earth is no longer the centre of the universe, not even a particularly special planet, but that doesn't diminish its value. It enhances it. Our world is precious precisely because we know how rare and fragile habitable worlds might be, how unlikely the chain of events that led to our existence, how extraordinary it is that atoms arrange themselves into patterns capable of contemplating their own arrangement. The fragments of 3i's Atlas, whether natural or artificial, remind us of both our cosmic insignificance and our cosmic importance. Our response to interstellar visitors like 3i Atlas reveals something profound about human nature. Despite all our conflicts and divisions, the appearance of an object from another star system unites us in wonder. Scientists from different nations collaborate to study these visitors. Amateur astronomers around the world turn their telescopes skyward to catch a glimpse. Children learn about them in school, expanding their conception of the universe and their place in it. These cosmic messengers remind us that we're all crew members on the same spacecraft Earth, sharing the same harbour of home in the vast cosmic ocean. The fragments of 3i Atlas that continue their journey through interstellar space carry with them a record of their encounter with our solar system. They've been changed by their passage near our sun, their surfaces altered, their volatile components partially depleted. In a sense, they now carry information about us, about our star, about our corner of the galaxy. If they eventually encounter another star system with curious observers, those observers will learn something about us from studying the fragments. We've become part of their story, just as they've become part of ours. This exchange of information through physical objects travelling between stars represents a kind of slow, patient communication that might be common throughout the galaxy. Each star system leaves its mark on passing objects, and those objects carry that information forward to other systems. Over millions of years, this creates a web of connections, a network of shared information that doesn't require deliberate communication or advanced technology. It's a natural internet of sorts, connecting star systems through the patient wandering of cosmic messengers. Our harbour of home is enriched by these connections, by knowing that we're part of this larger network, even if we're the only conscious participants in it. Every meteorite that falls to Earth potentially carries information from another star system. Every comet that graces our skies might have siblings orbiting other stars. We're not isolated, but integrated into the galaxy's natural processes of exchange and connection. The fragmentation of 3i Atlas was a visible demonstration of these usually invisible connections, a reminder that our solar system is not a closed system, but an open one, constantly exchanging matter and information with the broader cosmos. The possibility that some fragments of 3i Atlas remain in our solar system, perhaps orbiting quietly among the asteroids or resting on the surface of some moon, means that future generations might have the opportunity to study them directly. Imagine a future mission recovering a fragment, bringing it back to Earth for analysis in laboratories that don't yet exist, using techniques we haven't yet invented. What might we learn from such direct study? Would we finally be able to determine whether the object was natural or artificial? Would we discover messages encoded in its structure, or would we find only the natural randomness of cosmic chemistry? The questions raised by 3i Atlas will likely outlive us all, long after everyone alive today has returned to the atoms from which we came. Future humans might still be pondering the nature of this interstellar visitor, still searching for other fragments, still wondering what it meant. This continuity of curiosity across generations is one of humanity's defining characteristics. We build upon the observations and ideas of those who came before us, and we leave questions and mysteries for those who come after. The fragmentation of 3i Atlas is now part of this grand tradition of inquiry that connects past, present, and future. As we settle deeper into contemplation of our cosmic home, it's worth reflecting on how the possibility of extraterrestrial intelligence, whether confirmed or not, changes our relationship with Earth. If we're alone, then our planet is the only known harbour of consciousness in the galaxy, making it infinitely precious and worth protecting at all costs. If we're not alone, then Earth is our unique contribution to galactic diversity, our particular expression of the universe's capacity for awareness, equally precious and worth preserving. Either way, the fragmentation of 3i Atlas reminds us of our responsibility to our harbour of home. The environmental challenges we face take on new dimensions when viewed from this cosmic perspective. Climate change, biodiversity loss, pollution. These are not just practical problems, but cosmic ones. We might be destroying the only known living world in the galaxy, or we might be failing in our responsibility to maintain our part of a galactic community of living worlds. The fragments of 3i Atlas, dispersing through our solar system, witnessed a planet in transformation, a world where one species has developed the power to alter global systems, but hasn't yet developed the wisdom to use that power carefully. Yet there's hope in this cosmic perspective as well. If humanity can unite in wonder at an interstellar visitor, perhaps we can unite in protecting our planetary home. If we can collaborate across borders to study objects like 3i Atlas, perhaps we can collaborate to address global challenges. The same curiosity and intelligence that allows us to detect and analyze interstellar visitors can be applied to understanding and solving our earthly problems. Our harbour of home is worth protecting not just for ourselves, but for the cosmic story we're part of. The legacy of 3i Atlas extends beyond its scientific value to its cultural and philosophical impact. This interstellar visitor has become part of our collective imagination, inspiring art, literature, music, and dreams. Children who learned about its fragmentation might grow up to become the scientists who finally answer the questions it raised. Writers and artists inspired by its mystery might create works that help humanity process what it means to live in a cosmos where such visitors are possible. The comet has become part of our cultural DNA, another chapter in humanity's long conversation with the cosmos. As we drift towards sleep, carried by these cosmic currents of thought, the fragmentation of 3i Atlas becomes a meditation on fragmentation and wholeness, separation and connection, the particular and the universal. Each fragment went its own way, pursuing its own trajectory through space, yet they all originated from the same source, shared the same history, carried the same cosmic heritage. In this way, they mirror humanity itself, divided into nations and cultures separated by geography and ideology, yet sharing the same planetary home the same evolutionary history, the same cosmic origins. The harbour of home we return to after our cosmic journey is both smaller and larger than when we left. Smaller because we've seen Earth in its true context, a tiny world orbiting an ordinary star in a vast galaxy. Larger because we understand that this tiny world is connected to everything else, that we're part of a cosmic story billions of years in the making, that every atom in our bodies has travelled across the cosmos to be here, now, arranged in patterns capable of contemplating their own existence. The fragments of 3i Atlas that survived their solar encounter are now far from the sun's warmth, returning to the cold darkness of interstellar space. They carry with them whatever secrets they held, whatever messages they might have contained, whatever purposes they might have served. But they also carry something of us, the record of our observations, the echo of our wonder, the evidence that in this corner of the galaxy, consciousness arose and turned its attention skyward, seeking to understand its place in the cosmic order. Perhaps that's the ultimate meaning of 3i Atlas and objects like it. They remind us that the universe is knowable, that through patient observation and careful thought, we can understand cosmic phenomena that seem at first mysterious or even impossible. The fragmentation that seemed so puzzling when first observed now fits into our expanding understanding of how objects behave in the extreme environment near stars. Whether natural or artificial, the comet followed physical laws we can discover and comprehend. This knowability of the universe, this correspondence between the human mind and cosmic reality, is perhaps the deepest mystery of all. Our harbour of home is not a final destination, but a temporary refuge in an ongoing journey. Earth is where we evolved, where we developed consciousness, where we first looked up and wondered about the lights in the sky. But it's not where our story ends. The same curiosity that makes us study objects like 3i Atlas will eventually carry us to the stars ourselves. Future humans might encounter the fragments of 3i Atlas somewhere in interstellar space, might finally solve the mystery of their nature and origin, or they might discover that the galaxy is full of such objects, that what seems extraordinary to us is actually commonplace on a galactic scale. The comfort we find in our harbour of home comes not from isolation but from connection, not from certainty but from mystery, not from having all the answers but from being able to ask profound questions. The fragmentation of 3i Atlas raised more questions than it answered, and that's as it should be. A universe that yielded all its secrets easily wouldn't be worth living in. It's the ongoing mystery, the continuous discovery, the eternal quest for understanding that gives meaning to our existence. As you drift off to sleep, let your mind rest in the profound peace that comes from accepting our place in this vast, mysterious cosmos. We are small but not insignificant, brief but not meaningless, alone perhaps, but not lonely. The fragments of 3i Atlas have dispersed through our solar system and beyond, but the wonder they inspired remains, settling into our consciousness like cosmic dust, enriching our understanding, expanding our imagination, connecting us to the grand story of the universe itself. The harbour of home we inhabit is a good place to be, a beautiful world perfectly positioned to observe and appreciate the cosmic drama unfolding around us. Whether 3i Atlas was a natural comet or something more, its visit reminded us of our good fortune to be here, now, aware and wondering. The universe has given us the gift of consciousness, the ability to observe and understand, to question and discover, to find meaning in mystery and beauty in the unknown. Tomorrow the sun will rise as it has for billions of years, warming our harbour of the home, enabling the complex chemistry of life, providing the energy that powers our civilization. But perhaps you'll see that sunrise differently now, knowing that the light warming your face has also warmed visitors from other stars, has caused ancient ice to sublimate and fragment, has revealed cosmic mysteries we're only beginning to understand. Every sunrise is a reminder that we're part of something vast and wonderful, something that includes interstellar comets and possibly other intelligences, all of us sharing the same physics, the same chemistry, the same cosmic heritage. the story of 3i Atlas is far from over. Its surviving fragments continue their journey through space, carrying their secrets into the darkness. Future interstellar visitors will arrive, each one teaching us something new, each one raising new questions, each one reminding us of our cosmic context. We'll develop better instruments, more sophisticated theories, deeper understanding. Perhaps we'll finally answer the question of whether we're alone. Perhaps we'll discover that objects like 3i Atlas are messengers from other civilizations. Or perhaps we'll find that the universe is even stranger and more wonderful than we currently imagine. But for now, in this moment, as you drift towards sleep, you can rest in the knowledge that you've contemplated one of the great mysteries of our time. You've joined the centuries-old tradition of humans wondering about their place in the cosmos. You've travelled in imagination from the formation of an object in a distant star system to its fragmentation in our own. From the possibility of von Neumann probes to the reality of our beautiful, fragile, irreplaceable Earth. You've participated in the grand conversation between humanity and the universe, adding your wonder to the collective curiosity that drives us forward. The harbour of home awaits your return from these cosmic wanderings, welcoming you back with the familiar comfort of Earth's gravity, atmosphere, and life. But you return changed, carrying within you a broader perspective, a deeper appreciation for the cosmic connections that bind us all, a renewed sense of wonder at the mystery and beauty of existence. The fragments of 3i Atlas may have dispersed, but the impact of their visit remains, rippling through human consciousness like gravitational waves through space-time, subtle but profound, changing everything while appearing to change nothing. Sleep now, cradled in your harbour of home, surrounded by the atoms of ancient stars and recent visitors, protected by an atmosphere that shields you from cosmic radiation while allowing you to see the stars, blessed with consciousness that allows you to appreciate it all. The universe continues its patient unfolding. Galaxies turn in their stately spirals, stars are born and die, comets fragment and reform, and somewhere in all that cosmic activity, on a small blue world orbiting an ordinary yellow star, you rest, you dream, you participate in the universe's attempt to understand itself. The mystery of 3i Atlas remains, a gentle question mark written across our sky, a reminder that the universe still has secrets to share, wonders to reveal, connections to forge across the vast darkness. Whether harbinger or happenstance, messenger or coincidence, the fragmented comet has become part of our story, and we've become part of its story. Two patterns of matter and energy intersecting briefly in the cosmic dance, exchanging information, sharing wonder, continuing on their separate but forever connected paths through space and time.